structure. When you have an objective that is a complicated one, that no one individually can achieve, you need to organize yourself, and you need to, plan ahead some of the tasks so that some results are available when they are needed. You also need to deal with the fact that some people will compete for results, because science is a competitive field, and you want to make sure that this competition is as fair as possible. It doesn't, pushes people aside for irrelevant reasons, and I think that's what a consortium is for. The consortium is really there to try and organize this activity that is research, when the goal that you have set to yourself is not one that can be reached individually. And for instance, determining whether dark energy exists and what it is requires many observations, analysis, simulations. All of this cannot be done by individuals or even by small groups. They have to, because of the resources that you need, and just the creativity and the invention that you need to bring forward. So you need to be more than a group or an institute. You need to gather people, because you don't know really where the good idea will come from. And the consortium is there to try and organize this so that we can reach that goal within a finite time. So I'd say that's mainly the difference. But now if you talk to the consortium member and ask them how do they do their research, I think that's a question that I can ask to you, and you can describe how you do the research, and I'm pretty sure they will say, well, that's how we do it as well.
By individually?
Yeah.
Yes, I'm not in a consortium, but I'm doing my research individually. But I'm using the data comes from the consortiums, for example, Gaia data. To use their data is important because, for example, we have an observatory in my country. We can observe open star clusters and we can get data. But how can I say? How can I describe? It is a. Sorry. I don't know how to describe. Maybe I can continue later. Just confuse a little bit.
Yeah, of course. One thing I thought about too was that it, of course, the need for these large consortia depends on many things. Two of them is which area of research it is, of course, which field, and the second is also the specific research question or the specific research problem. So I'm doing research in theoretical physics, and for theoretical physics you don't need as many resources, at least technology-wise or equipment-wise. You just need a blackboard, that's it. So the need for these large consortia is not as big, as at least directly in theoretical physics. However, a lot of ideas in theoretical physics are sparked from actual data and from experiments. And right now we're at a point in theoretical physics where there is not a lot of data, at least in like very fundamental theoretical physics. We're at a point where there is not a lot of data that can help us draw conclusions. So that's why we need these large consortia like the Euclid Consortium to get more big data and to push these boundaries experimental-wise as well.
We'll just ask one of the questions, because it's, I think, maybe the biggest clash in the concept of consortium, that's the competition. What your feeling with the competition on your proper research, and how perhaps for consortium, how consortium help in that in regulating that competition?
Well, sorry,
Go
do
ahead.
you mean like the competition within a consortium or between consortia versus individual research?
The competition within the consortium, or
Okay.
just within your community of researchers.
Okay.
I think just to maybe to clarify, there is competition in the sense that, for instance, you may want to be the first to discover this object or say something, and then there is something which is intrinsic to science, which is the scientific debate. When we want to establish results, we debate with people who have a different opinion, a different interpretation, a different theoretical explanation for a phenomenon that we see. And so one of the questions that I can see here is whether or not a consortium is efficient with respect to that scientific debate, because the consortium is going to publish its results with a single voice. Euclid is going to say that W is -1, which means that the dark energy is the cosmological constant. And you would say, well, has there been a scientific debate? If the Euclid consortium, which is 80% of the cosmological European community, says this, hasn't it killed the basis of science, which is to debate among ourselves whether this or that interpretation is the best? And what maybe you don't realize is that this debate takes place within the consortium. What we do is, when we say we plan our research, we say, well, Euclid was built to elucidate the nature of dark energy. So one of our objectives is to publish in 2030 a paper saying dark energy is or dark energy is not this. But we are going to get there exactly in the same way as any other research endeavor, which is to have a number of teams within the consortium that are going to push forward their interpretations of what the data is telling us, and we are going to have this debate inside the consortium, just in the same way as we do in the general community. But in the end, we will form a consensus, and that will be the Euclid paper.
A follow-up question: will the people from outside the consortium, but still in the same area of research, will they get to hear about these discussions that take place before the final publishing? Because if not, then you need a large enough consortia in order to hear as many perspectives as possible, right?
I think the correct answer is no, in fact, because we want to release the data on which we base our analysis at the same time as we release the publication. But the objectives we have are, I think, too ambitious. So we will not succeed in doing this. So the data will become public before we are able to converge on the final interpretation. And so, in effect, there will be competing organizations, competing teams having access to our data, who will be able to manipulate it and try and interpret it in a different way. But still, if you're part of the consortium, and I'm part also of the editorial board, which is overlooking all the publication process, there is a lot of discussion and debates, scientific debates going on inside the consortium to reach the state where we say, okay, this is a result of Euclid, and we are putting it out. So the competition and the debate exist inside. I see there's a question over there.
My question is this kind of exclusion, is it not dangerous? It could lead to a scientific monopoly.
Can you define what you have in mind for, as a scientific monopoly. What does it mean for you?
Let me just, without the mic, it's fine, it's fine. If you withhold the data to be able to publish your paper, it's, of course, it's your data and you need whatever you need to be able to keep researching. But if we want to keep the as open as possible, it's not bad for our collective to have this competition and not like others.
Just for the diffusion in direct, so if I correctly interpret your question, is that fair to keep the data closed within the consortium, where you are waiting for open data research within the total community of cosmology, for example?
Is it smart?
Yeah. Is it fairly intelligent?
Yeah, two comments. First of all, they do release the data eventually, so everyone can interpret them, right?
Yeah, if you, all of these experiments, and you were mentioning Gaia, all of these consortia experiments, they release all of their data. And they actually release it. That's why I said we were going to fail in producing the papers before the data become public. We have a relatively strict schedule of releasing our data, which which leads to a period of generally no more than a year when all the data has been acquired and it is not public yet.
You were talking about the year 2030 now.
About?
The year 2030.
Yeah, but it takes actually 6 years to make the Euclid survey. I mean, to acquire the data, it's started now in 2024, and it will be complete in 2026. And we will release the first year of data in 2020. In 2030, we will have completed the survey, but we make a first data release next year, then another one in 2026, then one in 2028, and another one in 2030. So, and in fact, that's the model. All of the collaborations, all of the big consortia that acquire data, in astronomy at least, they all release their data. And in fact, I think the astronomical community has organized itself quite early on to standardize the data so that all of it can be ingested in what we call the virtual observatory, so that you can actually re-observe the sky virtually using all the experiments that have existed so far. So I think that's quite important. It's a big constraint for us, for all the data processing system. And I think it's fair as well that there is a period during which this data is proprietary, in the sense that it gives a certain priority to those people who have worked to create the data, but it's actually a small priority, because 1 year to analyze cosmological data is really short.
Also, I mean, science on all scales is like this, that you focus on your research question, and maybe you have collected your own data, and maybe you've just simulated something, but regardless, you keep your research kind of secret until you publish it, because that's the time when you can be sure that what you've done is actually well presented and there are as few holes as possible and so on. So you need this period before publishing where you can just be confident that you're able to work on your research without anyone else trying to do the same thing.
A consortium. Is it like easy to get into grapple with that and then do like
So in general, a consortium is not a club. It's not complicated to enter a consortium. Another thing is that it's in general also completely impossible to enter a consortium and grab the data. Euclid is producing 800 gigabits of compressed data per day, and to process it, we have 9 supercomputing centers running every day. So, as an individual, this
go back to the question of did you feel, 3 of you, but especially 2 of you that are in the study right now, like bad competition, something, yeah, malfunctioning?
Yes, sure. There's a huge competition in the area. Actually, there's one goal. We, as become a scientist, we are scientists, we are astronomers, and we want to understand the evolution, formation of our universe, how it is formed, how it is evolved, and how it is going. And that's our problem, that's our basic goal. But on the other hand, there's a huge competition around this problem. And in my education, in my PhD education, for example, I'm handling with open star clusters to understand the formation and evolution of our own galaxy, because if we understand our galaxy, we understand the other galaxies. And if we understand the other galaxies, actually we understand, we start to try understand the universe. I'm observing them, and I'm doing some analysis about open star clusters, and eventually I need to do some research paper, right? And then published. But one side, I'm an individual researcher and small research groups, and other side, there's a Gaia consortium. They have big advantages because they can access all data firstly, and data comes from later for me. And does it fair? In a way, maybe not, but it's advantages if you belong consortium. Yeah.
Yeah, that's interesting. Perhaps Nicholas.
But you have not decided to join a consortium yourself, right?
Did you repeat?
You have not decided to join any consortium yet, at least, right?
No.
So what's your reason for that?
Actually, I don't. Does it work? Actually, I don't have a chance to join a consortium. If I have a chance, sure, why not? I would like to be a part of such a huge consortium.
Maybe if there anyone that had a experience or having, unfortunately, experience of that bad competition, or even that dominance of consortium on his or her research, maybe. So no one. So maybe we can go back on your answer, and you said that you didn't have any chances to to join a consortium, when can you advise to consortium to let more students get into that?
Actually, I don't know. I have no idea what to say about that.
Someone has an idea?
So it's a bit strange that I would answer this question, because I'm no longer a student. It's been a long time. We do take in students inside the Euclid Consortium, and but students are never isolated. And maybe that's one thing that changed, but it changed a long time ago. Students always have an advisor. They have a master thesis advisor. They have a PhD advisor, and they get in the consortium through that. What we did initially, for instance, and I think it was a very positive change. Initially, we said, well, okay, PhD students and master students, they don't need to apply to the consortium because they are de facto members, because their advisor is a member, and this sort of made them invisible, which was not a very smart idea. It gave them also a sort of strange membership status, and since as we evolved, we developed a lot of tools which relied on being a member of the consortium. We've changed that completely, and now the students are full members as the rest. They have the same privileges as any other scientist. The only thing that we require is that they are connected through their advisor, and I think it makes sense because the consortium is a complicated structure to understand. It's not something that when you get into research, this is not really what you expect in terms, because there are lots of structure. We think ahead about what we're doing, and we take decisions, and we break down things and attribute tasks to people. So this is at first glance, it appears as very different from what you expect from research, where you set your own agenda, you do what you want, what you think makes sense. Here, you have to keep that frame of mind, but you have to try and insert it into a bigger project. And this is sometimes a bit complicated. How are you going to fit as an individual inside a project which is collective, without losing completely the fact that as an individual, you have your own creativity, you have your own desire of going rather in this direction than that direction. How is it going to fit? And it's the task of the consortium structure to identify how we are going to make that work. That's why the students, we think, need to be connected to someone with more experience to try and get their mark into this structure and start navigating it.
Maybe I will ask to both of you, do you feel like you continue as an individual researcher, because none of you are part of a consortium? So can you see your future without a consortium? Can you, yeah?
I think it depends on the specific field. So the area of research that I'm interested in does not really have a need for these large consortia. But you also have other branches of theoretical physics, like simulating scattering reactions of fundamental particles, and the stuff they do at CERN, for example. And in that case, you need lots of resources. And then I think it's just a good thing that you have these consortia, because then as an individual or just as a researcher starting your career, you have the opportunity to apply to that and to work on these enormous, very, very difficult, very complex problems. Whereas before you didn't have these consortia, and then these questions, these research questions were just not available. So I think it's just a good thing, because you can choose kind of which area you want to focus on, and the research questions that some of these consortia focus on are very, very complex research problems. So it's not really, you're not really available to do research on them individually, at least not on the same level.
And you?
Yeah, actually, in general, I agree with that opinion, but it depends on the research area mostly. For example, maybe in theoretical physics, you may not have been in a consortium. You can make your research individually. That's okay. It's cool thing. But in observation, on the other hand, observational astronomy, it's a good privilege to be in a consortium.
But you always have the ability to choose to join a consortium, or at least to try to join and to apply, right?
Yeah.
So, yeah.
It's not an easy thing to join a consortium. Maybe we can change the question. We can look at on the other side. What consortium expect the students like me, like the young researchers?
I want to react to the fact that you say it's not easy to join a consortium. I think it really depends. You know, Euclid, I'm going to often refer to Euclid. I've been spending the last 10 years in this collaboration. So, but okay, Euclid is having one objective, which is to elucidate the nature of dark energy. Okay, that's, if you're interested in that, that's great. But to do that, it observes 1/3 of the sky, and it observes everything that is in this 1/3 of the sky. So if in the data that we produce, there is something of interest for you, for instance, stellar population of global open clusters, I'm not so sure that we are going to observe that much because they tend to be a bit too low in the disk. But globular clusters, they are high above the galactic plane. And we are going to observe tens of them, and we are going to observe extragalactic globular clusters. So if you're interested in that, there is science to be done with the Euclid data, and you can apply to the consortium to participate in the exploitation of this aspect of the science. So I think this is the consortium exists because sometimes the resources you need, you cannot get them without an international collaboration. Sometimes it's not necessarily the resources, but the analysis power that you need, you cannot get it with a single institution. But then usually, and I think it will be the general rule in astronomy, the large experiments that we are going to make, they're going to be made for a few science objectives, but they are going to allow thousands of others. And I mean, Gaia, when you think about Gaia, what is Gaia? Is measuring positions and proper motions of stars. That's what it does. But look at what it discovers. You know, it discovers black holes. It images the structure of the galaxy in 3 dimensions. It does a lot of things which are more than just the measurement. And Euclid is the same. And the US is doing the Roman observatories that is going to do the same sort of things. And we call that legacy science. So we have an objective, but then we have legacy science. And if there are lots of things that it is enabling, and the consortium are open to scientists who are interested in that. And there you can do your own research. I mean, I don't know if we have time, but we can elaborate on what it means to me doing your own research. But you can do it.
Yeah, I will ask. Yeah, of course.
As I understand from you, you said that actually it's not as complicated as we thought to join a consortium, right? Yeah. If it is, I will try my chance to join Gaia consortium.
I know that Euclid is still recruiting. I don't know whether the Gaia consortium, since Gaia, I think is no longer taking, well, Gaia is taking data.
Yes,
so,
yes, it's
yeah.
continue.
So I'm pretty sure that it's still feasible to join the Gaia consortium.
Maybe I will ask to Niklas and then both of you, what because we talked a lot about the relationship between consortium and individual researchers, but we also have these incredible tools that is informatic and computer sciences and network, etc. So that is really facilitated by all the technologies. So we have seen an evolution between from the way you are doing science. So what is your expectation for the future of doing science and research with keeping that in mind of the evolution of the technologies?
I mean, from the theoretical perspective, I really look forward to getting a lot of new data from these big consortia and getting a lot of new experimental and observational insights that can drive the creativity in theoretical physics. So that's one more indirect aspect of it. And I think also another way in which theoretical physics can benefit from these large consortia is when it comes to really, really heavy simulations and computations that need to take place. And then you also don't have enough resources in just one research group, so you need to get together and you need to collaborate a lot as well. And yeah, as technology advances, then our computational ability advances, and so we're able to analyze more complex and more real problems.
Maybe one of you?
Yeah, I think if you look at the Euclid is only feasible because now we have the capacity to analyze its data. If you take a Euclid image, there's about 10,000 objects in that, and there will be maybe 30 or 40,000 different Euclid images. So it can only be analyzed through automatized system, machine learning systems. Euclid is essentially a statistical experiment. So every advance that we make in signal processing statistics is going to feed into the analysis of Euclid and is going to make it possible. And on the other side, there is indeed simulation. I think this is a very important aspect of what we do. We're trying to elucidate what is the structure of the universe, and we're doing it by observing objects in the universe. And these objects have their own physics. So to separate the physics of the object from the cosmology, we need to understand exactly how the universe evolves, including the physics of galaxies and stars. And so there are lots of simulations that need to be developed to compare simulations with observations. So all the computing powers that we are acquiring and the facilities that we have in developing these simulations, all this feeds back into the analysis that we can do on the Euclid data. So what I think is that typically, these data, such as the Gaia data, they both have a sort of instantaneous value. You acquire this data, you analyze them for a purpose, and then they have a long-lasting value because there is more information than what you have been able to extract in that at time t. But 10 years later, you have more resources, you have a different understanding of the physics of galaxies that you were using as tracers, and we are going to make new simulations and new comparison with the data and extract more information. And I think this is valid everywhere in astrophysics. And that's why, in my opinion, that's why the astronomical community realized very early on that storing the data, archiving them, and making them interoperable was very important. Because what you have observed once for a purpose may serve another purpose in the future. You don't know that.
Maybe if what will you accept of the technology to to improve the way you are researching in the future? What can you expect from the new technologies and from the new new way to make science? What are you accepting for the future of sciences, of researchers?
You say in time in the developed technology, what I'm expecting through my research. Right now, I'm studying about open star cluster because I want to understand how my galaxy evolved, how my galaxy formed. But the technology is getting more developed. All these questions will have an answer right now. For example, why we use Gaia data? Because we want to map our galaxy. 3D map our galaxy, but in our galaxy there are some places that we couldn't see. Maybe if we go outside our galaxy, of course we are not doing that now. But if the technology in the future will let us to do that, maybe we can find different answers about our galaxy.
Okay. And maybe I will also on the tech level of research, not only the technologies you are using to acquire data and to make a analysis of data, but also to just work with, because in like every job you are using your computer to just send an email, and what because the way we are doing research evolved a lot from the past century. Because of this evolution, we gathered more. For example, do you think that consortium may be possible without the telecommunications that we use today?
I was going, when you first formulated your question, I was thinking, I don't think research as an activity has changed that much, in the sense that if you strip it down from the technological aspects, yes, we are using computers instead of rulers to compute things. Has it really fundamentally changed? I'm not completely sure, but you're right. I think in one point. A consortium such as Euclid cannot function if it doesn't have the right communication tools, and we've actually experienced that because it took us, I think, 7 or 8 years to figure out what were the communication tools that we needed to function as a effective collaboration. And it's because inside a large collaboration, exchanging information is complicated. In fact, if you think of it, Euclid is gathering 18 different countries. So as I said, there's about 1,500 researchers, going from students to more senior people, from people who are studying stars in our galaxies to people who are studying the structure of the universe. So there's nothing simple inside Euclid. Nothing is simple. Every time you want to address a situation, it's going to be, complicated because you need to talk to people with very different backgrounds and very different environments and very different habits. And so it took us really a long time to figure out how to structure the information, how to make it accessible, and what kind of tools should we be using to communicate among ourselves so that at any given time, everyone in the consortium knows almost the same thing as everyone else. And I think we're almost there, but that's something which is very different from what it was earlier, like 20 years earlier, when none of this existed. Even if email was already there, we didn't have the capacity to organize ourselves on that scale. And so these consortia didn't really exist, except in particle physics, and it's not a surprise that effectively particle physics invented the web, just because they really needed it.
I also think on the individual scale that the technology of digital meetings has really made a huge it's made a huge impact, because research is a fundamentally international and global endeavor. So you need to communicate with other research teams, and also a lot of the time research are spread out in so for example, the group that I'm working in is located in the United States, but some of us live in Sweden. So, and we don't have time to go visit each other every time we want to discuss something. And a lot of things are not possible to discuss over email. So being able to do these digital meetings, thanks to a lot thanks to the technology developed during the pandemic, I think it's made a huge good progress.
Lastly, if there are any questions or insights, maybe what's the place of technology in your research, if you want to add another point of view on that, or have any other questions? So, lastly, because we are running out of time, maybe you said that in your consortium, you were mostly able to prevent everyone, inform everyone at the same time, but you were like quite hesitant on that point. And what are you expecting to be more as technology maybe, or something else? And what can you imagine also in the communication within the community, because we have lots of articles each day and papers each day, and so maybe the communication have really blown up for by the new technologies. And how can we reorder that maybe to be more readable?
Well, I think we're hitting a human limit, in the sense that you know, if you want to make sure that everyone has the information that you want them to have, the limit that you're hitting is that you're going to push so much information to people, they will start disconnect. Just to recover their capacity to concentrate. I mean, we're making this experience every day. If you use social networks, and if you accept all the notifications, you're unable to pay attention to anything. And so what most people do is effectively cut down any notifications. And so what I think is, it's like in every it's an experiment by itself. What we want is, we want to reach a certain level of information transmission, so that we want most of the people to know most of the information they need to work in the consortium. But we know that we can't reach the state where everyone has all the information. Because if we want to do this, there'll be people that will be submerged by information, and they will just cut down just to stay safe. I mean, and so it's where is that limit? When you're sure that people have most of the people have most of the information. When we started the consortium, most of the people didn't have the information. That was our big failure. We had many different systems, wiki space, blog posts, and so, and everything was scattered without orders. And so the main obstacle to joining the consortium was to understand where is the information that I need. Now we have streamlined this, but we know that we will keep on having people coming to me just because I'm there, just because I'm their neighbor, or I'm in the office next door, and telling me, how do I do this? And it's written. If if you take a little bit of time, you can find it, but people will still do this, and you have to accept it. So I think it's like in every human endeavor, you have to understand where is the feasibility limit, try to reach it, but don't try to be perfect, because perfection doesn't work.
Maybe, Saval, you were wondering that you were thinking that it was quite hard to reach and to go in a consortium. Maybe, do you think that the lack of information communication on that level was a causes of that, of your impossibility to join if you wanted to? You just said, Mark, that there is a lack of communication at the beginning of consortium, because and that's make the joining process more difficult. And do you think that was what prevent you from joining a consortium?
Maybe that was one reason. Yeah, sure.
I mean, I've never thought about joining a consortium, but not because I think they're bad. I think they're really great, but it's not been relevant for me.
So thank you very much for this roundtable. I think we can applaud them. And now we have a little break of 15 minutes, and there will be two talks just after that break.
For the Gaia.
That's some new researchers
to know more about our universe and the amount of matter that contain. The motivation of my project is we know that the early universe predicts that the primordial density fields are Gaussian. Therefore, the two-point statistics will describe the information of the early universe. And we have the information, for example, the CMB. We only we have a bigger amount of information from the two-point correlations than the three-point or the four-point correlation functions. Also, there are some work that does with the 3-point and 4, but the amount of information is really small. And they enter in the nonlinear regime, and when this happens, the 3-point correlation function is different from 0 and gives us additional information than the 2-point correlation function. That's why in the other images, the 2-point correlation it's not there. Only the 3-point, which we have to use triangles, and the 4-point like squares. However, there are some problems to compute it. The first is the computational time. Imagine you have a distribution of galaxies and galaxies. So you will have to choose one of them, and for the next point, and you will have n-1 options, and for the third one, n-2. So it gives you something of the order n cubic. And if you have n of the order of 8, n cubic will be of the order of 24. So it's computationally really expensive to compute it. Fortunately, Exceed Sapudi, in his work 3-point statistics from a new perspective, present a different way to characterize those triangles, which is only use two sides of the triangles and the angle between them. Another problem is the photometric galaxy surveys have not had enough number of objects and neither the accuracy needed. As a result of this, we have obtained limited results on higher order statistics. And again, fortunately, exist projects like the Vera Rubin Observatory. This observatory will inspect very large regions of the sky and measure millions of galaxies in a small amount of time. And my project is part of the Mexican collaboration that belongs to the LSST, which is the Legacy Survey of Space and Time from the Vera Rubin Observatory. And the project involves 3 parts. The first one is the 3-point correlation function, the estimator. The second is the signal modeling, and the third one, the covariance matrix. And as the title says, I am more focused on the covariance matrix. And another thing that I want to clarify is that is more focused on scalar fields. Scalar fields like counts of galaxies. So we start assuming statistical isotropy and homogeneity. Isotropy involves that we can rotate the triangles, and homogeneity we can translate them. And one estimator that is homogeneous is the equation 1. And as I said before, we have to characterize the triangles only using 2 sides and the angle. The angle will be measured using an arbitrary axis, and we will have a point pivot, and then the 2 sides of the triangle. And using the equation 1 and 2, we can obtain the equation number 3. But that estimator was only homogeneous, and we have to do it also isotropic. So we have to integrate taking an arbitrary angle, and after a lot of calculus, trust me, we obtain these results. But we won't have only one triangle. We will have a lot of points. So we have to do it in different binning. In each bin, we will have points, and we will choose a point pivot, and the binning will have a characteristic distance, and again, we will measure the angle using an arbitrary axis. On the other hand, we know that the 3-point correlation function in Fourier space is the V spectrum, and again, we can characterize it using the 2 sides and the angle between them given by plane waves. And also, due to we are using plane waves, we can pass to this form. And also remembering that the 3-point correlation function is given at this way, and we can use the orthogonality again, and using the definition of Fourier spectrum and some properties of the Bessel functions, we arrive to the correlation function in the real space. As I see, I think that this is the connection between the Fourier space and the real space. And using simulations, as Professor Helen showed us, and also the theory, we obtain that they are similar, so we can use this description. On the other hand, we want to study our universe, and we don't have a laboratory in which we can create our own universe and evolve it. We only have the observations and the theory if we want to study our universe. So we need our likelihood function, which compares both the observations with the theory and the covariance matrix, which is this one. It contains the errors of our method of measure, and usually for the 2-point correlation functions, we use simulations, 1,000 of them, to obtain or have a good error. But for the 3-point correlation functions, you are not allowed to do it because the computational cost is really expensive, so you can do it. That's why I did it analytically first. And another, by definition, the covariance matrix is given by this equation. As I see, it's like you have a triangle and another one and have the mean value of them. So you will have the value of 3 sides and another 3. And with this part, you can make groups, 1 and half 1 and 5 terms like that, and 2 and 4 and 4 terms, and 3 and 3 and 8 terms, and 2 and 2 and 14 terms. As I said, most of the information comes from the Gaussian part, so I take more into account this part for the calculus. And finally, I found this expression only for the covariance matrix, which involves these integrals. Each of them has Bessel functions or of different order, 0, m, and m plus prime m. And the CL is the angular power spectrum. And also I have to do code. It's written in C. And to solve the expression numerically, we use the trapezoidal method with an adaptive mesh that takes thinner steps when the frequency of oscillation is larger. And a measure of the period of the combined oscillation is given by this quantity. In this case, we have the oscillation given by theta I, theta j, and r. And so the period will be 1 over the maximum value between r, theta 1, and theta 2, or theta I, theta j. And in this graph, I want to show you that the integrand, it's really difficult to integrate, taking different values for r, theta 1, and theta 2. And on the other side, as I said, we take thinner steps. So if we use 20 steps, if we use 200 steps, it doesn't matter if we use also 80 steps. The accuracy is the same, and it's important because we want a smaller amount of time in computing time. And these are the covariance matrix and the correlation matrix. And what is next? We have the estimator, the signal modeling, and the covariance matrix. But with the signal modeling and the covariance matrix, we also can do Fisher forecast and to constrain cosmological parameters. And that's it. Merci beaucoup.
Thank you very much. Is there any questions? No, perfect. You were so clear. So now it's the time. Sorry for the next round table. Okay. Please, Tala from coming.
Hi, my name is Talar Yontan. I'm from Istanbul University, Turkey. And I got my PhD about 4 years ago. Now I'm studying in the Istanbul University as a lecturer. So I will give a brief information about the galactic open star clusters, which contain my research subject, and I will give you information why we use the galactic open clusters and what is their importance and what is our main purpose to study these celestial objects. Actually, we want to investigate the galactic structure, its formation, evolution, and chemical evolution. So we decided to choose this object, and I will tell you why we are choose these objects. Now we can start ask what are the open star clusters. Open star clusters is a group of stars that formed from the same molecular cloud and bound with loosely gravitational forces together. They usually appear scattered and sparse in the sky. A typical open cluster may contain about hundreds or thousands of stars. Star clusters are important objects for the study of a wide range of the astrophysical phenomena. Open clusters are good astrophysical laboratories for understanding the internal structure and evolution of stars. And we can see the different types of open star clusters here. What is their importance? As I say, open star clusters are formed from same molecular cloud. Hence, ages, distances, and metallicities of the cluster members are similar, except their masses. And cluster member stars have different masses. These give opportunity to understand, to investigate the stellar evolution. And here, one of the example for open cluster called NGC 3766 in Centaurus constellation, and we can see in that area blue and red stars together, which means in this cluster they are different stars with masses, magnitudes, and brightness, and physically they appear blue, and it means this cluster is young cluster. how is the formation of the open star clusters? It is the same stellar formation. This image describes a scenario where a shock wave from a supernova explosion occurring at the distance of 20 or 1000 parsecs from a molecular cloud. This explosion impacts the cloud with shock waves, and these impacts can trigger the process of the star formation within the cloud. So the shock wave compresses the cloud uniformly, leading to the simultaneous collapse of various regions within the cloud. So the stars start to form, and the age range is narrow. The age differences within the cloud is around 5 to 10 million years. After the molecular cloud begins to collapse, this is due to the external or can be internal forces. Massive stars are first formed in the OB associations, which these stars are massive stars and first form in the cloud. Then, meanwhile, the collapse of the cloud continues and stars of smaller masses are formed. Once the stars are formed, if they can remain gravitational bound, they form open star clusters. Here is the other M67 open star cluster. We can see it contains both red and blue and different apparent magnitude stars together. This is the physical picture of this cluster. When we investigate this the scientific way, we should use the HR diagram, which is the mostly used diagram in the astronomy. We can see these stars represent the narrow morphology on this diagram. So hence we can investigate the structure of the cluster, which contain main sequence, turnoff, subgiant, and giant regions in the cluster. And it indicates the both stellar evolution and age of the cluster. And on the star cluster in the Milky Way, where we can find these objects, we can find these objects on the galactic disk. Open star clusters mostly found the spiral arms on the spiral arms and between the spiral arms, because they are young objects and star formation process is continued. So in our galaxy, dynamically star forming region is the galactic disk. So with this object we can investigate the galactic disk, because these objects have wide range ages, distances, so we can study these objects. Yeah, and how can we investigate the open clusters? Which methods do we use? We can investigate them photometric, astrometric, and with spectroscopic methods. Photometric methods are photometric. We use photometric filters selected within the different electromagnetic regions, and we reach from this data their color excesses, colors, absolute magnitude, and metastases. With astrometric methods, we reach their coordinates, positions, proper motions, and trigonometric parallaxes. With spectroscopic methods and with high resolution spectroscopic observations, we can measure radial velocity, atmosphere model parameters, element abundance, rotation velocity, color excess, stellar activity, and mass loss. And how can we use these methods where the data come from for these methods? We can get photometric methods individually in the observations or big data centers like from Gaia. And astrometric methods also we can get from the data centers and from the big data surveys releases. Spectroscopic methods are also like photometric methods. We can perform the observation individually, or we can get the data from the big sky surveys. And for this, we use Gaia mission. The Gaia satellite has been launched by European Space Agency in 19 December 2013. It aims to find out a three-dimensional map of the galaxy by analyzing high accuracy astrometric and photometric observation of nearly 2 billion sources. And first Gaia data release in 2013, and then we can achieve now Gaia data release 3, which is the last version of the data. And Gaia observes the solar system objects, stars near the Sun, Milky Way disk and bulge of the Milky Way, and nearly galaxies. So it contains a big and sensitive data for researchers. And these observations provide us kinematic properties and metallicities of the galactic objects, also hints for stellar revelation, formation of the disk components, understand halo and dark matter, formation of bulge component, dynamical processes of open and globular clusters, investigation of the structure, formation and elevation of the Milky Way. It has big data and we use this data. And one example of 32 open clusters investigated from the Gaia, second data release of the Gaia, and we can see the absolute magnitude versus Gaia colors, and these are open star clusters in different ages. This color bar shows the scale, denotes the different ages. Here we can see the young and old age star clusters in the one HR diagram. The youngest one is represented by blue color, and when the cluster gets older, we can see its turn-off point and subgiant, giant region. So it tells us about age of the cluster. And what is the distribution investigation of the distribution of the open clusters tell us? We can reveal from the celestial object spiral structure of the Milky Way, kinematic and dynamic processes of the open clusters, and galactic wrap. So with photometric and astrometric methods, what can we perform separately? We can determine the celestial coordinates and structure of the open clusters, member stars, and mean proper motion of the cluster, color excesses, metallicity, age and distance, luminosity function, present day mass function, and relaxation time of the cluster. With photometric, astrometric and spectroscopic methods, also we can achieve the same parameters and plus radial velocities, metallicities with from the spectroscopic surveys. And we can investigate the kinematical and dynamical way in the open clusters. We can perform these analyses, and we can detect the binary systems in open clusters, and we can determine the radial velocity also both clusters and both individual stars in the clusters. And what we do in the Istanbul University, actually we also perform our observations, open star cluster observations. We use UBV passbands for this in optical region, and we use the 1 meter diameter mirror, this telescope which located at the Tubitak National Observatory in Antalya, and also we have ongoing projects on the observations of the open clusters. We choose these clusters from the literature, and we take care of they don't have UBV observations, and they are less studied clusters. And which parameters do we determine? The structural and astrometric parameters, these central coordinates, center stellar density of the cluster, background stellar density, core radius, and proper motion components also. And we determine the fundamental astrophysical parameters, color excesses, metallicity, distance modulus, ages. Because of the open clusters contain a group of stars that have similar properties, for this the cluster can be presented. These fundamental astrophysical parameters can be determined from the group of stars, and so it gives more sensitive results us. And some of the examples from our observation in the Tubitak National Observatory, these are different open star clusters you can see here. This is the images of the cluster, and we transform these images to numerical data. So then after that, here we can see our V passbands and G Gaia passbands, number of stars according to their apparent magnitudes, and structure of the density profile of the clusters, which means in the center of the cluster the stellar density is high, and when we go through the from center of the cluster, the number of stars start to decrease. Here, this profile gives us tell us about structure of the cluster. So for this all analyses, we should select the member of the cluster truly, because it is important to select these members because they have the same properties in the cluster. So for this, we use their astrometric parameters from Gaia satellite, and we use their proper motion and trigonometric parallaxes to calculate their membership probabilities, and after that we choose the cluster's members. We do this to achieve accurate astrophysical parameters, actually. And we can see here in the diagrams, in vector point diagrams, we call that, constructed from the proper motion components of the stars, and color scaled circles represent the number of stars with high probability. We can see these stars are concentrated in a narrow area, and the gray dots are represent the represent the stars with lower probability members. And this is the HR diagram constructed from UBV and Gaia data. We can see the members of the clusters represent the one line, and we can see the main sequence and giant star, which is important to obtain the age of the cluster. Here is the determination of the age of the cluster. We use again HR diagrams, and we constructed these diagrams from both UBV and Gaia observational data. So we choose the models, isochrone models, for the determine the distance and age of the clusters. And we take care to these models represent the member of the stars well. And in Turkey, what we do with observations, we do photometric and spectroscopic observations performing in TÜBİTAK National Observatory and university observatories, the other university observatories in Turkey. Photometric and spectroscopic data from international observatories and data from the data centers. We use these all data together. And we are not only study individual open star clusters, also open star cluster studies contains binary systems, exoplanets, and PhD theses, stellar cosmology, metastasis. These all subjects contain the studies. Yes, that's all. Thank you for your listening.
Perfect, thank you. Is there any questions?
Thank you for the talk. What influence, or rather, by studying these open star clusters, what do they tell us about the formation of the galaxy? Or are they? Is there any relation at all between the history of the galaxy and where you find these clusters and the ages and whatever?
These clusters are found in the galactic disk mostly, and they are good traces of the galactic disk. So the number of clusters represent similar properties, so we can estimate their metastasities, distance, ages in accurate way if we compare with single stars. And their ages, distances are spread a wide range. So we do calibrations between metastasities and the distances of these objects from the galactic center through the more distant. I forget the word. Yes. From center, the galactic center, outwards the galaxy. So we expect the metastasity of this distribution change from all the distance, and in the galactic center there are star formation, ongoing star formation, and these stars is metallicity more than the solar vicinity. So we can say that if the metallicity is high in the galactic centers and getting lower through the outside of the galactic center, we can tell this the galaxy disk is galaxy disk formation is caused by two informal model of the galaxy. There are too much formation models and theories for the galactic disk, and we can test these models with making correlation between the astrophysical parameters, like distances versus metallicity, age versus metallicity, distance versus metallicity. We investigate these changes and tell about the models that presented for galactic evolution and structure and formation. Okay.
We can take one last question.
Were you able to reconstruct through Gaia data the whole, the 3D velocity field in some clusters? Through Gaia, were you able, besides the radial velocity, to reconstruct the plane of sky velocity of some stars, of some clusters, and be able to study the full dynamics of the cluster?
Also study their dynamics. This tell us about the both cluster dynamics and in the galaxy dynamic internal. It's tell about internal and external effects. How these things affects the cluster. We can understand this with the Gaia data also, because we use the radial velocity from the Gaia data, and with this data we perform kinematical analysis and dynamical analysis also, and we try to understand how these clusters react in the galaxy according to their ages and metallicities. Okay.
Thank you very much. Now we have a 10-minute break, and after that break, there will be, so you have some cakes and drinks outside, just at the left when you are quitting the room. And so just after this little break, you will be able to attend the outreach session with Yumna Majid, Gabriel Delevrin, and Maram Kairé. So they will explain more about the outreach in astronomy. Thank you. And just there is key that were founded in the room. So if anyone recognize them, just tell us. Thank you. Pakistani astronomer, or at least outreach developer. And so you will present us the astronomer outreach practices so in Pakistan, and so you have 15 minutes, and it will be a pleasure to hear you.
Keep track of time. Hello, everyone. I don't know how to say it in French, but in my language, we call it Assalamu alaikum. And I am very grateful to ICAY and SAF for inviting me all the way from Pakistan to share my work that I do in Pakistan. So I am founder of Exploration, which is a non-for-profit organization working in Pakistan for the last 8 years to bring wonders of cosmos to the Pakistani classrooms. The most frequently asked question from me is that why you wanted to be an astronaut or why you love stars. And mostly people think that must be I have seen stars and tried to count stars in my childhood. That's why I fell in love with space. But that's not true. Every time someone asks me that where your story begins, this is a painting that I did a few years ago, and this is what I show them. It's a baby astronaut in a womb. I always say that that is how it started because I know that I always wanted to be an astronaut since I was born. So I think from that shift from wanting to become an astronaut to becoming a space educator is quite interesting. When I was 14 years old, I was in a classroom full of 60 girls. All of them wanted to be a doctor. And when my teacher asked me, what do you want to be? I stood up and I said, I wanted to be an astronaut. So everybody started looking at each other because they had no idea what an astronaut is. So my teacher explained what an astronaut is. And then she said, Yumna, you cannot be an astronaut because there is no such thing as space. And if you try to go up there, you will die. So that was quite harsh coming from my own teacher. And I was discouraged. I was just 14 years old kid. So I was discouraged and I made no friends. I used to speak to nobody. So I was just like the wonder kid from the movie. But not only that, when a few months later, I changed my section. I moved from the excellent section to another section and I was playing with my friends. I made new friends. An ex-classmate came asking me, Yumna, is that you? I said, yeah, that's me. She said, but you're normal. I said, yeah, I'm normal. Why are you saying like this? She said, since you never talked to anyone in classroom and you had a dream to go to a place which does never exist, we thought you are a mentally disabled child. So that was my moment of realizing what is the role of an educator, a teacher, in building or breaking dreams of their own students. So I think that 14-year-old Yumna somehow decided that she has to change that perspective for Pakistan. So yeah, and at the same time, till that age, I used to think that this is just a camera trick and a desktop wallpaper. I had no idea that this is an actual astronomical phenomena. And once I discovered, I was 15 and that's quite old to know that this is not just a desktop wallpaper. But after knowing that this phenomena exists, I got to know because I saw it on a timeline on Facebook from a medical student who was also into astronomy. And since that day, I started arguing with my parents that if somebody else, it's the typical Asian family where you have to prove to your parents that if somebody else is doing it, you can also do it. So after knowing a lot of things, that how astrophotography works, how astronomy works, I joined a lot of organizations like online pages. That quest started and I basically tried to reach out every single non-for-profit organization online which does not have any problem with my nationality. So that's how the work started. This picture here, where I am in red, it's from 2016. I started literally from my home. I used to gather kids at my home and teach them about space. We used to debunk space myths because a lot of people still think that Mercury is the hottest planet and Pluto has been blasted somewhere in space, but that's not true. So all these pictures, I started astronomy outreach without having a telescope. But in 2018, SSVI is an organization that literally changed my life. I am sorry if I pronounce his name wrong, but his name is Jean-Pierre. And in 2018, I won a telescope which is signed by astronauts. And it was a huge achievement for me to get a telescope. But once the telescope came to Pakistan, the customs was not allowing me to give me that prize. Excuse number one was, you are a medical student. By the way, I'm a medical lab technologist. I graduated 4 years ago. So first excuse was, you are a medical lab technologist and medicine has nothing to do with astronomy. And when I showed them my certificate in association with different non-for-profit organizations, the next excuse they gave me was, you cannot have a telescope because it is a terrorism tool. So that's me with my AK-47. Sorry. So yeah, and after getting the telescope, my outreach sessions started growing bigger and bigger and bigger. I used to put telescope outside a random building, at an orphanage, at a private workshop, at a school. But if you noticed, most of the sessions are done during the day because of two major reasons. One, the schools prefer activities that can be done during the day. Second, me being a girl who was not comfortable going out at the night time and putting telescope on the roadside. That is not something doable for me over there. And unfortunately, doing lots of record-breaking solar observations in Pakistan, I have quite developed an eye condition now, which is reversible. Even though you do it with a solar filter, please shy away a little from the sunlight. So yeah, it keeps growing and growing, and all these pictures that you are seeing from 2016 to 17, 18, this is 2019, 18, 21, 22, and everything kept growing bigger and bigger. I got featured in different books, got awards, went to NASA, attended space camp, met a lot of astronauts, got scholarships to attend different conferences, all on behalf of doing astronomy outreach in Pakistan. And yeah, we also grew not in just in terms of doing outreach sessions, but also in terms of team. Big things cannot be done alone. Initially, my organization was a one-woman army, but then I made a team. So before, our logo and the name of the organization was Exploration by Yumna, but then we kept growing bigger and bigger, and I realized that it shouldn't be just by Yumna anymore. So yeah, that is a short list of my achievements, and I would like to guess any of you, or not just guess, you can tell me what do you think, which one is the most amazing achievement. I won a lot of telescopes, I got a set of meteorites, including a piece of moon in Mars. I got featured in a lot of books. A magazine is all about me. Wherever I have traveled every time on scholarships and awards. So what? And yeah, in Pakistan as well, a lot of documentaries had been made, and also I have been honored by the Army of Pakistan as well. So what do you think, considering all the pictures that I have shown you guys in the previous slides, what do you think would be my biggest achievement? Yes. Close enough, the friends, yes. Any other guess? That was a good one, by the way. Any other? So my biggest achievement is the impact that I have been creating. Every time I receive messages from parents and young girls who tell me that we always wanted to do something related to space, astronomy, but we thought that nobody else in the country is doing it, so it's a very wrong choice. But now we see you doing it, which means our kids have a chance. Not only that, when, 5-6 years ago, when I filled the applications to apply for SSVI telescope in 2017, I wrote one line in my application that what will I do if I win this telescope? Why I want to win this telescope? Where I answered that if I win this telescope, I want to create a safe space for women and young girls in Pakistan to enjoy the beauty of the night sky. Fast forward to 2023, when I invited my team at my home and we were just having a tea party, I asked everybody that, tell me one thing that you really like about exploration, my organization. And one girl who joined us just a year and a half ago, she said that she loves how exploration is a safe space for her to share her passion for space and, without the fear of being judged. So for me, that was a moment of mission successful because she had no idea what vision I was having before making exploration. But deep down, I knew that we are getting there. Yeah. And quickly, so 1.5 years ago, we got, I don't know how to say it in French. I'm so sorry, but this is Marcel Moy Prize by French Astronomical Society. And luckily, that was given to me by a French ambassador in Pakistan. That was our first go-to telescope. So far, we have 2 manual telescopes which have a wooden mount. So having this telescope is a real big deal for us. And this is how we are creating the impact. In May 2024, our organization is 8 years old, and we celebrated our 8th anniversary by conducting a very large astronomy festival of 300 to 400 people in South Punjab. So we are not just in one city anymore. And yeah, this is, you can say, the first lighting of the telescope gifted to us by French Astronomical Society. Here you go. And yeah, we always believe in impact. So these are few numbers. We have worked with more than 80,000 students. I have no good record of how many online live sessions and interviews and podcasts we have given. But we are really glad that now Pakistan knows that there is their place in space if they really want to. So we have programs for primary and secondary school kids. We have programs for kids who are not in schools due to health challenges like hospitals. We also work with oncology departments. We have programs for differently able kids, special programs for girls. We want to train teachers as well. Not only that, but I'm also working on making programs which are edutainment program. For example, why a planetarium is supposed to be inside a museum, why you can't put it on a birthday party. So, edutainment. We have also programs for preschoolers because I don't know, but parents from now, they want their kids to be an astronomer when they're born. So a lot of demand came because why are you only taking kids who are 6 years old or above for 4 or 5 years? So we are also making sensory space play programs. And lastly, we are also having some research internships for high school students. That's a lot of work, believe me. And that is how, so all the work that we have been doing in Pakistan, these are the United Nations Sustainable Development Goal that we have been following, we have been fulfilling. So number 1 is gender equality, quality education, gender equality, reducing inequalities. Both of them comes under the domain of, you can say, making space more accessible to everybody, not only just for a specific socioeconomic class or not only for the kids who are in schools, but I'm trying my best to make it accessible for all in true means. And also climate action, we try our best that whatever material that we are using in our hands-on workshop, we somehow recycle it. And partnerships for goals, because a lot of work that I have done in Pakistan is on behalf of or with the help of the international organizations that we are affiliated with. That was quite a surprise for me when I landed in Toulouse a week ago. I had a conference to attend in Cité d'Espace. I think that's the only French word that I'm pronouncing so well now. I hope so I'm pronouncing it well, but I was just roaming around the museum when I saw that in the other part of the world, my work is featured up there, and my work is now part of one of the exhibits at Cité d'Espace. That was quite a big emotional moment for me, and very grateful to French Astronomical Society and ICAY for making this moment possible, inviting me to Toulouse. Otherwise, I am always living in imposter syndrome, but now I feel like, okay, we're doing good. And yeah, there is one question that in Pakistan, there are a lot of robotics club, and people, when they ask about what I will be doing in my workshop, there are always expectations that I might be making some big stuff like connecting wires and Arduinos like robotic workshops. But I tell them that astronomy is always an observational science. No matter what, you cannot bring the galaxies and the stars and every planet inside a classroom. So you have to use arts as a medium to teach astronomy. Yeah, I wish I could have a baby City del Space in my city one day, but for now I am working on a traveling space museum. Currently, we have a few telescopes and a set of 13 meteorites. We have made an exhibit out of it, and I travel with this small space museum in different cities of Pakistan to give space experience to kids all around Pakistan. But we are still looking for other material like inflatable planetarium or VR headsets and 3D printers, which will help us print. How to say that? We print those. We haven't done that before, but we want to make those tactile plates, which will be very helpful to teach astronomy to people who are blind. Yeah, what are the challenges? We have been doing a lot, but we are volunteer based entirely. We do not have a sustainable model because people think that if a subject like astronomy is not bringing food to the table, it is not worth paying for. And people these days, unfortunately, prefer to invest in maybe food and nice clothes, but not in education. So it has been very difficult to have a very sustainable business model. Secondly, we lack equipment as well as facilities. So far, we work remotely. We do not have a venue. So even having a venue would be a great help, because if a school is not agreeing to have workshop, what we can do is we can help private workshop where anyone who is interested can join. But even the offices and venue locations are quite expensive. I don't know. Let's do this exchange. Do you guys do you guys think that in Paris maybe you can rent an office for 500 euros for a month? Is there any place that you can rent for 500 euros a month? Well, in Pakistan you can rent an office in just less than 500 euros a month, and not only that, you can actually hire an intern in the same budget to share your workload. So that is how much difference it is. Lack of funding, lack of human resources, lack of training as well, because most of the time it's me who is leading the workshops, and it gets tiring because if I am traveling, nobody else is leading the workshops. It gets really difficult. But also another problem is lack of motivation. When something is voluntary, you do it like 1 year, 2 years here. Not everybody is crazy like me doing it for 8 years. But yeah, lack of motivation and then sustaining a team of volunteers is also very difficult. And yeah, these are a few or maybe a lot of people who have featured us, who have appreciated us, loved us, and partnered up with us. And yeah, that's our social media if you want to follow and support. And yeah, thank you, shukriya, merci. That's the French I know.
Perfect. Thank you, Yumna. Is there just one question, because we are running out of time? No? Okay, so now it is time to let's pick Gabriel Delorin. Gabriel Delorin is the chairman of the Astronomics Ungdom, so the Swedish Astronomical Society for the youth.
All right, thank you, the organizers and everyone, for letting me hold this little presentation for y'all. It's an honor, and I think I hope that we'll have a good time. So as Alexandre said, my name is, as I have learned to pronounce it in French, Gabriel Delegations, and I'm the president of the Swedish Astronomical Youth Association, Astronomisk Ungdom, as you can see our logo there. So now you know 2 words in Swedish. And so the background, I guess, and I think this image speaks a lot of words. Just so you know, if I seem to stutter, I am not nervous. I'm completely calm. It's just a medical condition, okay? So, like the previous speaker said, we all, at some point in our lives, look up to the sky and are fascinated. I do think that you don't have to be an academic to appreciate the night sky, right? You can be a carpenter, you can be an economist, even a politician. And it is something for us all, but it is not accessible to us all. And we need something to really capture everyone and give everyone a decent chance to pursue an interest they perhaps didn't know that they had, and a potential they perhaps couldn't explore themselves. So that is why in Sweden we have AU, Astronomisk Ungdom, Astronomical Youth, and we provide this possibility to the Swedish youth. Our purpose is to promote interest in astronomy and space exploration among young people in Sweden. And our mission is to provide each member with a community centered around their interest in space, learning opportunities to deepen and broaden their knowledge of space, and personal development to enable each individual to advance their space journey themselves. This is actually in our statutes. So a brief timeline to give you some perspective. We were actually founded in 2012, then as a simple organization with members who are like individuals like yourselves. We grew quite rapidly, 100 members in just a month, and then we continued to grow to 1,000 members, and then you see the umbrella, and that signifies the fact that we went from a single organization to a federation of associations. So Sweden has this great and really established culture of creating associations and umbrella organizations and stuff like that. And it was just a question of time when a federation for space for young people would be founded, and was here in just before 2016. And then you can see that we had 7 member associations in 2016, 15, 2017, and we continue to grow in total members, and 24, 46, 50, and then something like COVID happened, and we had a little bit of stagnation, and now we're back, and these question marks I will answer in a bit. So our member associations, who are those? Well, they typically come in 4 different categories. We have local organizations, high school, university, and themed organizations. And they are completely autonomous and have their own boards, statutes, finances, activities. And we as a federation are here to help them, but not only us as a federation. Oh yeah, these are just some pictures to actually not only have texts. So this is some local organizations all across Sweden. I can actually say this also because I only have like 15 minutes to give this talk, and there's so much I want to tell you. I won't be able to tell you everything, but with me I do have like 8 more people as part of the Swedish delegation. So after this talk, if there's something you'd like to discuss, just hit them up and they will answer everything right there. Some of them are even here. So yeah, this is the local activities. We have some high school activities. They're shooting rockets apparently. University, they're building rockets, bigger rockets. And then we have themed organizations like astrobiology, astroparticle physics, and stuff like that. Even a sci-fi organization, study trips to CERN, some Nobel dinners, some nice activities for young kids about astrobiology, what is life and life in space. And then, of course, we not only have our member associations, now we also have district organizations. So Sweden is a very, like, I forgot the word. I'll just use Swedish so you'll learn. Avlång. So it's a country that's very avlångt. And therefore, it is actually quite tough, quite a challenge to really be present, if we're not talking about the digital medium, to be really present physically everywhere. So to aid us in that, we've actually established 6 district organizations to as it says, they operate within their geographic areas to further our like big interest with the federation. So here is Stockholm somewhere. A lot of the people from our delegation are from here, from Gothenburg. I'm from here, close to Denmark, apparently. And how many of you here have read Dune, by a show of hands? Yeah, all right. So actually our council assembly of the district is called Landsrad, which is from Dune. We do that a lot because it's quite fun to take some references that we all space nerds like. Some regional district activities. We celebrate Christmas. We shoot more rockets. We have some nice conferences. And the Federation, of course, has a board of directors. This was actually, we don't look like this on a normal workday, unfortunately. But this was actually just before we went to last year's after party of the Nobel Prize ceremony, which we were delighted to be invited to. And those medals are medals we give ourselves. And I'm not joking. Perfect, and that's our duties. Let's continue. We also have an observer, like it's the highest patron, with focusing on the Federation's affairs and protecting our interests and our goals. And this an incredible woman who has worked with outreach in astronomy in Sweden for 30-40 years. And we're honored to have her as our first observer, Dr. Marie Rådbo. We have an office, personnel, 4 of them right now. This is our founder and now Secretary General, Mikael Ingemyr, and then we have a operations developer, associations developer, project leader. This is our Secretary General, our boss. How many of you here has actually seen the US show The Office? By show of hands, some of you. Okay, so you know the middle manager, Michael Scott. His name is actually also Michael. He bought this to himself, the world's greatest boss cup. He also did this, but he's fine. And then the office helps us do some national activities on federation level. So just to name a few, some camps for children, study trips. This is in La Palma, one of the Canary Islands, camps for young adults, some scholarships to Portugal and Norway, and then some international competitions, astronomy Olympiads. We actually, I believe, received Sweden's first medal, a bronze medal, quite recently, which was quite exciting. So we're doing something right, or the other countries are slacking, I don't know. And then CanSat, where we encourage people to build their own little space probes, which are sent up. Space Summer Research School, a big program that we have in the summer, where we have Sweden's first astronaut, Christopher Iglesang as our headmaster, and some very prominent lectures, and a very intense and fun program which inspires many, and a lot of the students who are actually part of this are then part of the volunteering group that enables us to do everything. Nice pictures. Other fun stuff, let's brag some more. This was from an event that we were invited to with Saab, the military manufacturing company, which also does space stuff, because they have like the test pilot who is now Sweden's 3rd astronaut. We have Jessica Mir, which I saw on the photo on the previous talk. She's also part Swedish. And some nice big conferences. We actually also received a ceremonial flag from the Swedish king, His Majesty the Swedish king, on, I believe, 2 years ago on the Swedish National Day. It was broadcasted live, so my mom and everyone saw it, and they were like, "Whoa, you're a celebrity now!" But unfortunately, Michael, the Secretary General, he stands like right in front of me, so you can't even see me. But like, yeah, it was my one moment, and it's lost. So now, ever since then, I'm working to get that second chance. And we received some diplomas. And then the timeline, yes, what happened here? Well, that's actually quite fun. So we have proven ourselves time and time again. So we managed to sign a launch reservation agreement with the Swedish Space Corporation. And we actually sent up 2 experiments to space, to low Earth orbit, and then they went back again, that were designed and manufactured and studied by people, young adults from the ages of 6 to 20. So we had this incredibly ambitious program where we went out to schools to lecture about this opportunity, and the youngest children, they couldn't obviously build the probe or the CanSat type experiment, so they designed the patch, and then when they got like for the older children, they requested some of the things that we should film inside the experiment, and the older ones even helped build it. So that's where Sweden's Young Space Program is born. So here we have some nice pictures where I signed some nice contracts, and then this was Aurora 1, that's what we call the space experiment. This is the second one, and I want to show you a quick video because it's quite nice actually. So this went up to space, went back, we had a little camera in there to like show the ones that participated in this project, which were like over 1,000 students all across Sweden, and this is just the second one. We think that the third one will get at least 5,000. So I think I have here like a nice video. So if you look there, we should see some nice microgravity effect on our logo right there, or perhaps, yeah, look. It's almost floating. Yeah. Okay, never mind. Tough. These are, yeah, so it was the Swedish Space Corporation that made this possible, but then we have a lot of other Swedish partners. It all relies upon volunteering. As is said, we even give more medals to others, not just ourselves, in the federation. Really fun, some pictures from our annual meetings, leadership courses. And we get a lot of news coverage from this because the interest is high. So, for example, here is Svea, the name, 8-year-old, has designed for the stars. So she was the one that designed that patch over there, which was sent to space. Yeah, that's fun. And of course, the effects are also on the individual members. So these are just some of the members that have been with us and been volunteering and inspiring others, been inspired themselves, and are now part of the beginning stages of their own space career, basically. So some of them work at Saab, at ESA, at CERN, at FUI. These are some Swedish companies that are very prominent in the space industry. And then the future, yes, so here's me signing some more contracts and stuff. So we the one thing that I believe has made this federation so incredibly successful in this short amount of time, not being without its challenges, is that we who are volunteering, who dedicate our free time, our spare time, to the point where everything else becomes spare time, we are incredibly ambitious, and we want to make things happen right now. We cannot wait. We don't feel we have the time. So that ambition really is a very prominent characteristic within our federation. So we were founded in 2012. We became a federation in 2016. Soon, we think that we will have a so what am I pointing at? It's just dirt. No, this is like 1,000 meters above sea level on La Palma, in which we intend to build our own observatory for approximately 300,000 euro, I believe, if we get the funding or win the lottery. And this will be like, it will be now possible for young Swedish students to reserve some time with this telescope to remotely observe the night sky from from actually, I believe, Europe's darkest night sky and the most prettiest. So here is my vice president, also Niklas, looking impressed. There's me signing some documents. And we also believe, actually, we will get some space on a satellite in like some years, so that they will also be able to like observe some atmospheric phenomena from our satellite. Some nice logo there. We are also in the process of establishing Sweden's like first space foundation, which will provide funding long term for our goals, and of course ICAY, which we're very proud to be a part of, and are looking forward to continue making it grow and reach its absolute potential, because I think that with ICAY we can learn from each other. There's so much we can learn from Pakistan, there's so much we can learn from Mexico, there's so much we from Sweden want to share, and from all over the world, how we actually engage our societies and impact individuals as well as the society in total. I think that communication and just free dialogue is so incredibly valuable, and the results that can come from it. So that's why I encourage you all to really like just ask that question that you perhaps are 50-50 about asking, because it can lead to something great. And then perhaps we can make sure that not everyone has to observe the night sky alone. We can be, there's actually two people there, it's a bit dark. We can be more, we can be together, helping each other and dreaming together. And with that, merci beaucoup. Yeah, I guess any questions, if there is any, or we can take it in the break.
You are doing my job. That's perfect. Any questions? Perfect. So now we have the honor to welcome Madame Kaire to a presentation about the Senegalese Space Agency. That is the General Director. And so it's a very honor and pleasure to welcome you, ma'am.
Wow, you're so beautiful. Well, just 10 seconds. It works? Okay, so first of all, I would like to say I'm really sorry. You know, I just come straight from Toulouse for the communicating astronomy to public, and I just don't have the time to change this part of my, so I'm sorry. Yeah, you can laugh, it happens. The second thing is that I don't speak English at all, so I'm going to switch in French. I discussed with my friends just behind there, Mr. Sylvain and Francois, and saying that I just have to read on the website that this conference is in English and in French. And I already chose to speak in French. And knowing that I don't speak English, do you agree with me if I switch in French? No? Let's do a vote? No? Okay, so keep on speaking in English. Well, I am very happy to be here with you. Just one moment. Okay. I'm very happy to be with you today to share our experience from Senegal. And for those who don't know where Senegal is, it's just the western point of the African continent. And I am the General Director of the Senegalese Space Agency, a very young space agency, running its first year. It was created on March 23. But before that, we start doing a very long journey to arrive by creating this space agency. And this part of the story I would like to share with you began in 2006. We were watching an eclipse, a partial solar eclipse in Senegal. It was in 2006 on March. And we just noticed that the public was very interested in what we were sharing with them with this eclipse. And this is the first group with whom I decided to create the Senegalese Astronomical Association called ASPA. And it is the first astronomical association recognized by Senegalese state. And we start with this sort of equipment running across Senegal, trying to, for the first point, trying to train teachers. It was the beginning, you know, when you are in a country where astronomy is not very popular, you need to start by training teachers. And this is what we start doing from 2006 to 2008. This is a sample of the kind of exercise we used to do with teachers, some stargazing at the night, but a lot of training in how celestial bodies move around the sun and so on, some basic astronomy. And we help them to multiply the information in their schools and all around the country. So this is many activities we had in Senegal. Sometimes it's very specific. Here you have the school called Prytanée Militaire. They are training to be a sort of Saint-Cyr here in Senegal. And maybe a lot of officers in Senegal, in Senegalese army, are coming from this school. And it was important to have this kind of communication with them. And solar activities and so on. But the fact is that we decided not to stop, even if there was difficulty to have a means for doing our activities. We keep on running and running around the country. Another part of the story, and maybe one of the most important points, was to have opportunity to discuss with the population, not only through schools or universities, but to discuss with all the Senegalese population, but also the parents. And you know, I would like to share just one number with you. It's 16%. 16%, can you imagine what it means for a country like Senegal? 16%, 16%. Do you know? Maybe the number of, any idea? No? Well, you know, the major exam in Senegal, the most important for students is the baccalaureate. And you know, we are making a lot of effort in our country to develop ourselves. But the fact is that there is only 16% in scientific field for the baccalaureate. How can you imagine a country making investment, a lot of money, a lot of effort, if only 16% are interested in science in your country? And this is why we are fighting, using astronomy, trying to change the mind. For that, you need to discuss with the parents. You know, when the mom or the dad asks to the boy or girl to go and do something which can give you money quickly, it will not be astronomy. So we need to discuss with them, telling them that the development is a very long travel. We need for scientists in our country if we want to develop Senegal. And this is why we use this kind of activities to communicate with the parents. And in 2008, we start a new activity called Festival d'Astronomie Saint-Louis sous les étoiles. But there is a lot of name for this festival. Saint-Louis under the stars, Saint-Louis to the stars, Saint-Louis on the stars, and well, a lot of, because you know the guy who was the artistic director want to change the name sometimes, and it was funny, you know, having for the next edition the name changing. But the fact is that it becomes the most important activity in astronomy in Senegal. For 10 days, we move through the city of Saint-Louis on the north of Senegal. And we make a lot of activities for 10 days. And it was very, very interesting. And sometimes we have the chance to invite some people from France and other countries to share their experience. You know, doing these activities like Saint-Louis sous les étoiles make us maybe having the chance to host someone who is very special to me, Mr. Hubert Reeves. I think that you all know that we just come to lost Hubert Reeves. And I started being interested in astronomy when I was 12 and reading the book Patience dans l'Azur from this guy, and having this wonderful chance, you know, to receive Hubert Reeves in Senegal changed maybe my life. And in 2009, for the International Astronomical Union, it was the year of astronomy in 2009, and Hubert just accepted to come and visit Senegal for this event. And, you know, this is day he arrives in Senegal for a conference at the University of Dakar. We had around 2,000 persons in the auditorium, and we share a lot of activities also with Hubert. And just have to say that it was so nice. And at the end, we finished to attract the attention of Senegalese media, the press, national press and international press. And the magazine Ciel et Espace in 2012 just write this very nice article about our activities in Senegal. It was around 5 pages in this magazine. And, you know, when you do so in the major cities in Senegal, Dakar is the capital, Saint-Louis was the capital of Senegal before the independence. And we keep on moving from Dakar on the western point of Africa, moving to Saint-Louis, coming back to Dakar, Saint-Louis, Dakar, Saint-Louis, and people start asking, why are you keep on doing your activities only in major cities? We are in the center in Kaolack or in Tamba and so on, and we are interested in astronomy because we learn a lot of things about what you are doing. So this is why we decided to write the project of the space bus in 2010, and as usual, it was difficult, very difficult to convince authorities, to convince sponsor to give a hand for making this happen. So the concept was created on 2010, and we wait for 4 years before having funding for doing this travel around Senegal. So we move from Dakar to other regions of Senegal in 1 month, non-stop. So it was, at the beginning, it was very interesting. But you know, when you arrive, maybe at the end of the tour, knowing that you start on, for each step, you start at 8 in the morning, and you keep on sharing knowledge and things with the population. This is the equipment we use for the space bus tour, and this is what we had for each day for 1 month, non-stop. At the end, you know, the first day people are on the bus and singing, dancing for, you know, when you move from a city to another. The 5 days before the end, you enter on the bus and everybody's sleeping. And if you don't want to maybe to be sick at the end of this tour, we just used to put some medicines in the bottle of water, and you have to drink it for the day and to stay, you know, alive. So it was at this moment, I think that it was the most important activity in all Africa for promoting astronomy. So you have a lot of pictures here. Some exhibitions, conference, stargazing. We asked to the people to come back from 8 p.m. and watching the stars with us, with their parents. And it was a nice moment also to convince the parents how important it is to let their children do astronomy or science if they want. In 2000, it was in 2015. In 2016, we just add a new part of the project called International Conference Women in Science. It was very important for us to discuss with young girls in Senegal and to tell them that it is possible for a young girl in Senegal to dream about stars and so on. If you want to be an astronaut, it is possible. If you want to be an astrophysicist, it is possible. So we go at the Great Theatre of Senegal with around 2,000 young girls from all the country, and give them as role model some women doing very nice things in science. So it was very nice, and I think that the next edition will be in October. We are preparing to move around Senegal in 25 steps. The first one was 17 steps. For this new edition, it will be 25 steps. For 1.5 months, we are going to move all around Senegal for the new space bus. So maybe we will ask to some of you, if you want to come in Senegal for 1 week, and I see your smile. If you want to come and maybe try this experience, it's just amazing. Having 1,000 children around you and sharing your knowledge in astronomy is just something incredible. So if you want to be with us for this event, it will be in October and November in Senegal. I will discuss with Sylvain if we can find maybe 2 or 3% interested in joining us. You know, when you do these activities, sometimes you have unusual call or knocking on the door, and some friends just have a chance to discuss with people from NASA in Cape Town in South Africa. And I received an email from these friends called David Baratu saying, hey, NASA need for your help for some interesting mission. And it was for these 2 spacecraft. The first one is New Horizon. Just after visiting Pluto, New Horizon was moving straight to an Kuiper Belt object called Arrokoth. At those time, it was Ultima Thule 2014 MU69 Ultima Thule. And the second mission and the third one was for the new spacecraft launched in October 2020 by NASA and flying to observe Trojan asteroids in our solar system. You know, it is called Lucy. So what we did with NASA is to help them holding stellar occultation in Senegal. And it's something very crucial to help the spacecraft navigate and to arrive perfectly for the flyby next to the asteroid. So this is some pictures coordinating this mission with the former Minister of Higher Education, Research and Innovation, the Ambassador of the United States in Senegal, and Mr. Marc Bouy from the Southwest Research Institute. Here you have all the delegation meeting the President of Senegal. It was in 2018, and the President of Senegal accepted for our country to host this important mission for NASA. You have the former president in the white dress in the middle of this, and all the team coming from the United States, from France, and 21 person from Senegal. We fully take this mission in Senegal, which helped NASA to have a very good idea of the shape of this asteroid before the flyby on 2019. And hopefully they ask for a second mission for Lucy. And you have here the team, a wonderful team that makes success also the second mission. We have a lot of stars in this picture. The president of the, maybe you can recognize this ugly face, Mr. Sylvain Boulet, thank you so much for what you are doing for our collaboration. So another star, a new star, and called Eric Lagadec. Young older star called François Collat, just behind me. It's not safe to have François Collat behind you, but I'm trying. So you're now facing to this wonderful team. We keep on training young Senegalese people to host this kind of critical mission for NASA. And it was for an asteroid called Polymel. You have training session, preparing the equipment and the observers before the occultation night, and a wonderful video from Mr. François Collat. If you want to know what is an occultation, it's just like this. Have you seen it? Yeah? So it was just for Polymel. I think it was just 2 seconds, very quick, but it was a success. And the last mission for the asteroid Horus, you have the team here. Sylvain and François were also here, Anne Verbisquer from NASA, and all these Senegalese people, Mr. David Baratou. We start building a very nice cooperation for this mission. It is something very important for the next step, because my vision was to arrive to create a space agency for Senegal, and you need for strong human resources if you want to do so. So another point was to create with the collaboration between ASPA, the association in Senegal, and the French Association, Astronomical Society, SAF, and other partners like RFI and so on. We decided to create this webzine, which is the first one in Africa, and for the French part, it is in French. So it is a very nice idea to share information, what's going on Africa, through this webzine. And maybe one of the most interesting thing is that the partnership between this project and SSV, like you just come to say in Pakistan, you know, give to African young astronomers to win a telescope. So each 3 months there is a competition. You can win a telescope for your country, and trying to share astronomy with the people. And getting more and more impact in Senegal, being maybe contacted by the international media and sharing our experience, maybe give us the opportunity to have a connection with a producer who want to make a sort of biography, biopic of how I started being interested. Okay, how I started being interested in astronomy at 12, and maybe going on to all I just come to share with you. They decided to make this movie called The Star Chasers of Senegal. Oops, there's no sound. Sound, it's not a problem. I think that it just say, in Africa, astronomers are on a mission, and Marie Costaga, it's important in occultation. If you don't have the data at the right second, you don't have the data ever. And a dream of an astronomer trying to change the future of his country. I believe space is for everyone. I think that it is what he said. So the movie Star Chasers is available. Try to catch it on some platform online if you want to see it. And just after that, we asked to the president of Senegal if he would accept to be present for the first screening in Dakar. And it was just okay. You have here the first screening. The image is not very good, but the great theater was full. The president was there, and it was a magic moment. You know, when you keep on fighting from 2006, 15 years after, or 18 years, you finish to convince the president of the Senegal, who is foreign minister, to come in a theater and watch this movie. It was just something amazing. And at the end, the president just decided to create the Senegalese Space Agency. So my dream just became true. And it was amazing because at the same moment, the president decided to to appoint me as the first general director of Senegalese Space Agency. So it was more than expected, though. So, oh yes, you can if you want. So since the first screening in the US, so this movie was made by American TV Nova and Terra Mater, which is a part of Red Bull in Vienna. We have received a lot of awards. They are all very important for us. The last one is from the American Association for the Advancement of Science, which is supposed to be the most important science association in the world. And they give us the Gold Award for this movie in October 2023. So I was saying that the president decided to create the Senegalese Space Agency, which is the instrument for designing and implementing the national policy strategy for the study, research, training, promotion, and the development of space activity in Senegal. So it's a very large panel of activities. We are supposed just to be the interface between Senegalese states and all the space sector. We are going to do our best to make this mission succeed. I would like to no longer stay on focus on astronomy, but just to share quickly how we are planning to impact our country to achieve these sustainable development goals. So if you take a look to this dashboard, it is the last one in 2023. Like they said, it is from the United Nations. It's not from me. The overall score measures the total progress toward to mic finished. So in one word, if the 3, 2, 1, okay. So like they said, more the country is colored and more this country is doing good things to achieve the SDGs. And as you can see, the most colored part of this map is Africa. Is it okay for you? Or someone is saying yes. Oh, no, don't hesitate to say no. You know, the fact is that we spend all our time saying that space is not for Africa. Space is very expensive. Space is technology we don't have in Africa, and so on and so on. And if you maybe make matching these layers, this one is on 2009, 2015, the countries using satellites, the countries having space agency. If you maybe stack these layers, you can notice that all the countries which are doing good job for the SDGs are practically the same, using space for a very long time. And Africa keep on thinking that space is not for us because it's expensive or we don't have the technology. We have a lot of effort to do to achieve the SDGs. This is why the African Union start asking all the African continent to more consider space for their strategic development plan. And as you can see, this is a map showing how satellites are launched from Africa the last 20 years. We are about 50 satellites launched from Africa these last 20 years. So things are getting better. They start understanding that our priorities are depending on space if you want to develop our country. So this is why for the Senegalese Space Agency, we are moving straight to try to achieve these priorities for Earth observation, research, education, meteorology, climatology, and marine surveillance. Like, as you can imagine, I show you the place where Senegal is in the African continent. And for the west side, it's the Atlantic Ocean. So we have a lot of stuff to do for this part of our country. Communication for disasters and security and defense. And for each point, we will work with all this part of the Senegalese government. The main target is to create a very good interaction between the government, the state of Senegal, and the private sector to help for the development of digital and space ecosystem. We have a lot of good startups in Senegal for the digital ecosystem. Our job is to ask them to move to the new ecosystem we are trying to build up for space. If we can do so, we will, for the next years, produce a lot of services which will impact directly. Like you can see the SDGs for each priority we are running to. And this is a map. This is the map of our country, Senegal. Since 2 weeks, Senegal start being a producer for oil, and for the next months it will be the same for gas. We have a lot of offshore platform. We need to use satellites to make surveillance for illegal fishing, illegal immigration, surveying our platform for oil and gas, but also for security for the east side, and a lot of other priorities like you can see. At the end, what is important is to convince our government and all these startups and so on to keep on thinking services, to talk about services, and to produce services. This is how you can impact your economy. And this is how we want to develop this ecosystem, by producing a lot of services for Senegal. For our next step for the 4 years coming, the first year of the Senegalese Space Agency was the creation, installing the agency, doing some benchmark, recruiting people. We start working on our strategic plan with the cabinet PwC. We start the communication, international communication. For this year, we are waiting for the launch of the first Senegalese satellite in July. It is already finished. Yes, it is already finished. It will be launched in next month in July. We are planning to start the development of what we call the Senegal Space Valley. We will build infrastructures and assembly, integration, and test satellite in Senegal, reception centers, observatories, and so on. We will start the building of the second satellite in 2025, and the first constellation we already signed with a French new space actor called Prométhée to build the first constellation. The 2 first satellites will be built with Prométhée, and the 5 others will be built in Senegal directly by Senegalese engineers using this assembly and test building for. So on 2027, the launch for the second satellite, and the first constellation is supposed to be finished in 2028. It is not mentioned here, but my main target is to have a Senegalese satellite in a lunar orbit in 2030. It is possible, and we are going to do it. So take a rendezvous for this. We had, as communication, we had this significant opportunity to host the first space dialogue between the African Union and the European Commission in Senegal. It was an important moment for the Space Agency. We signed MOU with the European Space Agency. I see the logo of ESA somewhere in the shirt. It's you? Okay. So things are moving, and next step for the infrastructures, we are going to build the first observatories in the region of Kédougou. It will be shared between astronomy, astrophysics for a part of these observatories, and the second part will be for security and defense. We are going to use it for what we call surveillance de l'espace, to survey the sky. So this part will be with Senegalese army. And we already find a place. This is what we are planning to use. This is an image of the Center for Test, Assembly, and Integration for Nanosatellite. At the end of the day, what we want to do is to build a new city in Senegal devoted to space. What Silicon Valley is for technology in Senegal, what Toulouse is for Europe, for space. In Senegal, we have a brand new city called Diamniadio, which is practically devoted to digital sector. We are discussing with Senegalese president. The map is on his table. He is trying to find the exact place. We have 3 places identified to host this new city. If the president takes the decision, we will start building this new city. And in this city, you will find the headquarters for the Space Agency, the Center for Building and Assembling Satellites, Reception Data Center, Research and Development Center, Exhibition Centers, because we need to host a major event in space activity in West Africa, training and orientation center, data centers, innovation laboratory, an observatory, planetarium, museum, and incubators for startup. If you do so, you can give a hope for all these Senegalese young people to dream about stars, to dream about astronomy, space, and to have a chance to work in their own country, not only dreaming and leaving their country at the end. We want them to stay in Senegal. All those partners want to help us, have to come in this Space Valley and to do so. Well, to finish, one day in those missions we were talking about for the occultation, a guy called Sylvain Boulet just announced that there was something special for me. From that days, the asteroid called 1998 DW23 will be named by the International Astronomical Union, asteroid 35462, Madame Caire. So it is done, and I have this asteroid. Today, I'm leading the Senegalese Space Agency. I don't know for how long, and I don't know if I'm going to stay on this Earth. It's wonderful to live on this planet, but I don't know for how many times again. I would like just to finish my life trying to keep on working in the same direction, trying to work for the young generation. All we are doing is for the next generation. It's not for me. And this is why I decided to launch for the next month the foundation 35462, which is the name of the asteroid. This foundation with the slogan, I believe space is for everyone. So I will run everywhere if possible to find funds to help young generation to be interested in science. This is how we can develop our country. And this is the next step of what we already done using astronomy to develop and impact our continent. So thank you so much. And if you want to be a part of this journey, welcome to Senegal. Thank you so much.
Okay, so apparently there is no questions. So we are just putting in place the one table, and I'm inviting Mariam Kagé, Yunda Majid, and Gabriel Delorin to come join me for the second roundtable of this ICAY 24 on the topic of discriminations in astronomy, a challenge for the future. Okay, so on this second roundtable is on a topic that we are very concerned by, is about the discriminations. At ICAY, we are aiming at gathering everyone without distinctions and just to make us a union, because we are all living under the same sky. And that is really the major principle of ICAY. And that's why we really wanted to discuss about what can we do, we as a union of astronomers, of scientists, of students, of just passionate about astronomy, and also what can we do as just an individual that can fight against those discrimination that no one can agree on. So first of all, I would like to, of course, thank you for coming at this roundtable. Firstly, just a quick question about those discrimination we always heard about, but it's quite not often that we heard really about the story of people that was used to be discriminated. So maybe if you wanted to, maybe you start by just telling us a story, a little story about one discrimination that make you just feel strange and you didn't even think about that before being discriminated about that.
I think, I don't know, should I put this in the category of discrimination? But this one big misconception that I often see these days, the more I'm progressing in my work, the more I'm getting this is conspiracy theories, people thinking that space doesn't exist. Like I come across some people, adult, with making claims that, nah, the moon landings are fake, or no, these pictures of black holes are not real. So this is something which makes me go, wow. I mean, all countries who have all these big observatories and space agencies, do you think it's all for making science fiction movies? So this is something that I find quite strange.
This is a discrimination of astronomers as an entity. Maybe? Was strange to you before being discriminated about?
Well, I mean, discrimination in our society is not like only for the astronomers and space interested folks, and I haven't, I personally haven't experienced like um s- astronomy specific discrimination or something like that, but yeah, I mean, there's I believe in general in the uh STEM area, albeit Sweden is quite good at like having equality and non-discriminating environments. I do still think that there's a lot of work to be done in the STEM area to reach a completely non-discriminatory environment. But yeah, perhaps that wasn't a really good answer, but I haven't experienced something like specifically with astronomy.
Well, I think that is the same for me, and don't have example of discrimination, you know, directly. Maybe just sharing one frustration. When I was student here in Paris, when I just come to arrive, you know, they keep on advising you, well, this is how it works as a student in Paris. You have to do this. You have to find a job. You have to, and see an post saying, we are searching for someone for summer camp in astronomy. You know, when you start your observation in Senegal very young at 12 and build your own telescope. My whole life was designed in my head for astronomy. So when I received this this note saying we are searching for an animator for the space camp in the summer camp in astronomy, I just think, oh, it's okay. So I find my first job. So I write the answer, I send it, and few days after I received the letter, I was so excited. I open and they just say no. Okay, I say, so what is the problem? Is it because I have no experience or so on? But there was no details in the letter. They just say that you are not accepted. I share this experience because you are very damaged inside when you receive this kind of answer. And I share it because it is very important to keep on focusing on your target and never give up when you try to fight for something important for you. The place I share where the president was for the screening of the movie, there were a lot of students in the room, and I shared this moment saying them, if I were accepted as animator for this summer camp in astronomy, maybe I would not have the chance to be here today with the president and with all of you. Sometimes some doors are closed just because the best doors are open for you somewhere else. So it's not about discrimination, but it's sometimes how you can be frustrated, specifically when it is about astronomy, when people not understand really what is the meaning of what we are doing. When I was young in my city, usually people just pass in front of my my house seeing me on the ground watching the stars, and they just said, "Oh, okay, keep on watching the star. You will finish to be crazy." Or some people just ask, "Can you tell me the weather for tomorrow?" And they just don't understand what is astronomy, and they send you some bullet like this. So if you give up, it is definitely finished for you. So it is something I would like to share.
Thanks. What an advice. Maybe something that we can wonder as organizer of this congress, but also as people that are making astronomy live through outreach, through organizing events, societies, etc. What is the first thing you think about when it comes to helping fighting against discrimination? Of course.
What would be my advice? Okay, is it working? Okay. Yeah, so what would be my advice to do the first thing to fight against the discriminations, right? I think my advice would be to first be self-aware. Number one is to be self-aware, and then number two, be aware of what are the discriminations and where they are coming from. Sometimes there are misconceptions as well. So awareness part is very important, that you know what's right and what's wrong. So I think that would be the first step, that you need to identify that this is actually a discrimination, because sometimes something that would look like a discrimination to me would be a work culture in any other space agency. So you have to first understand your values, that where do you see yourself, that is this a discrimination or is this a not, and then you also have to identify the discrimination's root itself, that where is it coming from. Yeah.
I agree. No, it works. It works. It's fine. I completely agree with that. So we're talking about advice to the ones that could be discriminated, right? I mean, I think it's even 20, 50 years from now, I think it's naive to think that you can go like a career without experience some kind of discrimination. And more often than not, I mean, we should know that it is not always personal. It is not always like targeted specifically against you. It's a cultural thing, perhaps. They don't know better, or something like that. And you the simple answer, I believe, and it's simple and tough at the same time, and it is to be tough. I mean, you should be able to handle some discrimination, because you cannot go a life without it. I believe you're extremely privileged if you can, and yeah, just be tough.
To always think that the sense of discrimination can be very, very different in depending on our position. And you can talk about discrimination in an office. It can be in a school. It can be maybe in a whole country. The map I show you of our country, Senegal, and how we start our activities just between Dakar, the capital, and the former capital of Senegal in Saint-Louis, moving from this point to the second one for about 4 years of activities, was seen by all the Senegalese people as a discrimination. We are sharing knowledge about astronomy. We are sharing activities just with a part of the population, not with the whole population of Senegal. So it is definitely a discrimination. When you try to impact using astronomy, just to consider that it's not just for a part of the population, it's just for all the people you can impact. And this is why we decide to go through the whole country by the space bus. And it was just to maybe to correct an error from us staying in the major city of Senegal. And it was a discrimination. So for the next generation, I keep on asking them to be larger if they can. And this is why at this moment I think that we have more than 1,000 activities since the beginning of the association. And it is no longer concentrated in the big city, but it is everywhere in Senegal. So discrimination in small places like office, in a classroom, and so on. But discrimination can have another sense if it concerns the whole population.
So the idea of also of your advice is also to be self-aware of your proper actions that may be seen as discriminations, and you was not meant to. So maybe I don't know. I'm suggesting that maybe it's a lack of communication about what is or not a discrimination, especially in the astronomy, when we are of course talking about the sky, but because the science is something that gather everyone and bonds and link everyone, maybe it's also a way to create to exchange the information about that discrimination and what is that. So what's your insight about the communication problem on discrimination? Like, what is a discrimination? Do we talk enough about that in the astronomy world?
I think, so your question is about, yes, yeah, that's a really big question. Yeah, it's like a very open-ended one. So I think the problem is not in communicating the discrimination. The problem lies within communicating the astronomy correctly. We hardly have this subject in our schools, and mostly in underdeveloped countries, astronomy is being seen as hobby of elite people who can afford buying telescopes or who can afford the equipment of getting astronomy. That is something that negates the communication aspect of a discrimination. When a subject is communicated wrongly or it is not being communicated well, then it will create misunderstandings, and then whatever is being generated after that, then be it a discrimination or that's how maybe conspiracy theories are formed as well. So I think it's not about problem of communicating the discrimination, it's about problem of communicating the subject itself.
Repeat it a bit.
Do you think we communicate enough about discrimination in the astronomy world and within the astronomy societies, union, and organizations?
Actually, a really interesting question, because I mean, I I don't think that I can give the perspective that these two can, like specifically in astronomy. My association is it started with astronomy, but it's more like space and STEM in general now. We do a lot with like rocket science and stuff now. But from my experience being the federal chairman, i.e. the president for approximately 4 years now, and all my volunteering before that, is that the culture that we have in our association, and I hope that my delegation can agree with me, is that from day one, everyone is welcome. And we haven't actually made, I mean, perhaps we're kind of privileged or lucky, but we haven't made like specific programs for the ones that we feel are discriminated. For example, girls in STEM, or the ones that are in socioeconomic difficult areas in Sweden. We try to reach everyone, but once they're in, I mean, we do make some kind of subconscious effort to treat everyone equally, and I do think that that culture that we have, that we do not talk about discrimination if not absolutely necessary, means that you can come in as a girl, for example, in our association, I hope, and not feel that you get a label that, okay, you are a girl member. No, you're just a member. We don't care about if you're a girl, boy, or what else. That is not our concern. What unites us is space and our ambition for something greater, our dreams, and so on. And I do so. From my experience, like now speaking from myself, is that if you constantly talk about a problem, you're always gonna see that problem, and it kind of also cripples you, because you subconsciously see discrimination in everything, and it takes up so much of your brain time, I feel, at least. Now, this is not like, I'm not speaking as a president, this is from my personal experiences, and it has made life so much easier for me to like kind of actively not even consider me being discriminated if like it's not blatantly obvious and even someone has to tell me. I'm perhaps privileged that it has worked fine, but I do think that in an organization like ours, it has actually proven to be to work really well. We do have like a 50-50 between girls and boys in our organization, and we are over 5,000 members. And I do think that is some kind of testament that what we do works. And a side note to that, I do think that it is also because we value role models very much, and I do think that within our organization everyone can see some kind of older version of themselves, and I do think that that's important for everyone to feel not discriminated and a belonging.
It's already said. I think that it was perfect. Maybe one point is to notice that the best way to fight discrimination is not, I think, is not always crying everywhere that this is a discrimination, this is a discrimination, and so on. The word discrimination, as we know it, is not always a bad thing. There is a lot of act of positive discrimination right now all around the world. You can see either it is in astronomy or other fields, a lot of positive discrimination. When you decide to create an event showing role model, like he just came in a conference called Women in Science, it's a positive discrimination. You are not talking to all the population, you are talking to young girls in your country, showing them role models so they can accept that it is possible for them in the future to be like this person. So the fact of calling a group of young people in a city or in a country and to have a conference just for them is a discrimination, but it's a positive discrimination. It's not very bad. When you have some contests like Miss Science, in Senegal we have a competition called Miss Science to give award to the best students and schoolgirls in mathematics or physics and so on, it's a positive discrimination. It's to encourage them to make more effort in science. And this is why the government decided to especially give a help to the best young people in science to maybe move outside the country after their school to learn science if they want. And if you take two students having the same notes and the same background, if it is a girl and a boy, the government will help first the girl and after the boy. It's a positive discrimination. It's a discrimination, but a positive discrimination, because we need to encourage young girls in our country to embrace science. So discrimination is not always a bad thing. Fighting against discrimination is not just making a lot of communication in a point saying this is a discrimination, this is discrimination. You have to do more act of positive discrimination instead of just keep on crying or shouting that this is not good.
Upon that, because I do think it's quite interesting, because now we're using the word discrimination quite broadly, like not including everyone will just directly be discrimination. And I do agree that like we do need to target specific groups more often than not. But what was I going to say? I mean, I have the memory of a goldfish. So and it was personal, targeted. No, but I do think that, so yeah. No, I was going to talk about the I was going to talk about that example that you said about the the fact that the girl gets help first and then the boy, and I mean that once again is the thing that it's not personal. It's like on a broader level, and the thing is that you as a boy can feel discriminated. You can feel that, oh, okay, so that I need to be second in a list because society before my existence didn't work as it should, and now we have to correct that, and now they get the benefits, I don't, yada yada yada yada. You can do that, or you can just like shut up and do your thing. Yes, what I was also going to say was that I forgot again. No, but why discrimination is so hard to talk about is that you cannot like just slim it down to when not everyone is included or something like that, because I don't see a society in the future, if it's not a weird dystopia, where everyone will get the absolute same opportunity. That will never happen. You will have different different parents, grow up in different areas, meet different people that will enable you to accomplish things that others, perhaps smarter than you or whatever, will not. That's just how the world works. The thing is that the threshold we set is so arbitrary, and that is where the difficulties arise. When is it like discrimination? When is an opportunity not enough? When is an opportunity not honest enough so that everyone can make it if they want to? And should it be like everyone can make it? Is that really a reasonable goal? Because everyone will not be able to make it. So one of my favorite movies, which is actually set in Paris, is Ratatouille. And it's I think it's quite a nice lesson in the end, that the main characters kind of misinterpreted a message from the chef. So it's not that everybody can be a great chef, but a great chef can come from anybody. And I do think that there's some value in that not everyone can become anything, but you should be able to become something, and you should be able to have an honest opportunity. And yeah, I myself have a little sister who's now 5 years old, and I yeah, I mean, I want her to have all the opportunities possible. I want her to become whatever she wants to. She's not old enough to understand it yet, but I do think when the time comes, she will also realize that, I mean, some dreams are good to have because you need to strive towards something. But not everyone will reach the same dream, because not everyone can become an astronaut. That's just mathematically impossible. We don't have that many spots. But if we just take an analogy, I do think that everyone should strive towards a dream, even if it's not mathematically possible for everyone to become it. Because if everyone is on a ship traveling towards one star, and there can only be one to orbit that star, then when you get closer, other stars will appear. And I do think that you can jump star from the one to the next. Even if you don't in your life reach the star you want, you've at least lived a life where you actually have something to inspire you. And that is much more than most of the people in history have actually had.
Hello? Okay, can you hear me? Nice. I have a question about cooperation, because it's not necessarily about discrimination, but all of you three run organizations which focus on outreach and among other things. And as we are in an international conference, I was just wondering what your views on perhaps international cooperation within outreach to help each other grow and help increase interest in astronomy, like around the world. I was just wondering your views on that. Thank you.
Okay, now it is. Okay, so I think all the work that I have explained in my presentation earlier, all of that was done through international collaboration, international corporations. I knew nothing about outreach, what activities that I can do, what are the educational resources. My only way out was internet. When I grew up, I had no space toys, space books, libraries, nothing on television. And we got computer and internet very late as well in my home. So when we got the internet, that was my moment to explore every possible resource that I can, that how I can bring space and astronomy to Pakistan, instead of, if I want to like space and astronomy and it is not in my country, I should leave my country and go learn it somewhere else, because that is what I have seen my seniors doing. That if somebody likes space, okay, there's no space in Pakistan, let's move abroad. I wanted to bring it to Pakistan, and have been doing it through international cooperation for the last 8 years. And after this roundtable, I would love to have a conversation with both of them to see if we can have a collaboration. I believe for all astronomy organizations, mostly it's the international cooperation that works instead of local cooperation, because the community that you are working in, it's very difficult to insist them and to prove them that this is something really important. But the moment you get an international label, the moment you get an international logo on your poster, the worth of your organization, or maybe the worth of your work or whatever workshop you're offering, it just gets increased. It's just an impression of how world is being operated these days.
I part that you like become a bit more valuable in a lot of partners, potential partners' eyes if you have that international stample. I'm so sick and tired of regions and municipalities in Sweden just giving money to football games and not the astronomy. I love football though. Go Sweden. But to also give my unfiltered view on the question from Alexander, I do believe that when it comes to like space and astronomy, international collaboration is so like fundamental, because we as humans, as like the human civilization, we want to have a united endeavor into space. Like when we I mean, I know it was a space race, but when that American flag was on the moon, that was not just America, that was man. And I do think that that vision has to be something that could unite us all. I mean, a lot of astronauts, if not everyone on the ISS, talk about this overview effect that they feel when they stare down at the Earth, without the borders, without the man-made stuff, just the Earth. And I do think that international collaborations such as this, for example, to the participants, to everyone, will give some kind of feeling along those lines that this is not just in one country and we're not so different.
But I just come to say, and as maybe you have seen it on the slide, we started working with a small group in Senegal for the first 5 years, but at the end, it was very open, and we started collaborating with a lot of people for the festival Saint-Louis sous les Étoiles. And as you can see it also, building this webzine for astronomy in Africa with SAF and other partners is also another way of collaborating. The Space Bus hosting 6 astronomers from Paris to work with Senegalese people was also a sort of collaboration. And definitely science is collaborative, and astronomy, like we said, the sky is something just wonderful, because it's the, like Mr. Sylvain Boulin used to say it, le ciel est ce qu'on partage le mieux, c'est ça, Sylvain? Yes. Now you have to say it in English. I don't speak English. Look up to the yeah, and believe that space is for everyone. We have to work together. It's the best way maybe to share best practices. For the next edition of the Space Bus, we are planning to host about 15% from other countries. Some will come from West Africa, the Astronomical Association in Côte d'Ivoire, in Togo, in Benin, and so on. Mr. Jacob is here. We are going to ask to those leaders developing astronomy with us in Africa to come and join us for this next edition. We will do so for all the activities. Stellar occultations for NASA were very collaborative. You have 6 persons from France, 1 from Belgium, 2 from Burkina Faso, from the United States and Senegal, and so on. This is how you can impact more and more people if you want to do things in the good way. So at the end of the day, the world cooperation is at the center of what we are doing, all of us. And this is why I use this invitation for my last slide. If you want to do something with Senegal, you are welcome. Our country is known around the world as the country of Teranga. So Teranga is a word to say hospitality in our national language. It's the country of hospitality, so you can come at any time you like. And it is different of the song Hotel California. You know the song Hotel California from Eagles? Welcome to the Hotel California. So there is a sentence, you can check out anytime you like, but you can never leave. Our country is the country of Teranga. You can come, you can leave if you want, but it is always open for collaboration. So we are waiting for all of you in Senegal. I would like maybe to do activities with Sweden, with Pakistan, with all of you. This is how we can impact the next generation, showing them how to work together. And this is my final word.
Okay, so thank you, everyone. I think we can applaud them. So normally, and I just need to turn on the display if that is working. I think so. So normally we just received a few hours ago a message. So we are just going to install the next speakers. Thanks. A few minutes and it will be done.
Okay, please. We are going to resume, please. Thanks. So. So, well, welcome back. Please, thanks. So, I was saying, thanks. As some of you may have noticed, during the previous lectures and discussions, there was a name that was always coming back, and this name was the name of the International Astronomical Union. And so now the president of the International Astronomical Union would like to tell you some words that you registered for the ICAY. Thanks.
Greetings. I'm Deborah Elmgreen, president of the International Astronomical Union, which is the worldwide organization of professional astronomers. I'm delighted that so many of you are here for the inaugural International Congress of the Astronomical Youth. You are our future, and I'm grateful that the Société Astronomique de France has undertaken this initiative. Astronomy is deeply rooted in our histories and cultures, forging bonds across society. The universe as a time machine allows us to reconstruct our cosmic history, viewing distant galaxies as they appeared when they were younger, and inviting broad thoughts about our place on fragile Earth and our connection to the universe. Whether we're using the Hubble or James Webb Space Telescopes or the ground-based radio arrays and large telescopes of the future, the universe is available to everyone. The IU has 12,000 members from 85 member countries, including junior members who are early career PhD astronomers. Our mission is to promote and safeguard astronomy in all its aspects, including research, communication, education, and development through international cooperation. We have annual international specialized symposia and a General Assembly every 3 years. In fact, our 32nd General Assembly is in Cape Town next week, the first time in our 105-year history that it will take place on the continent of Africa. It will be a free open access meeting, so all of you are welcome to go to astronomy2024.org to participate virtually. To help with the goals of sharing astronomy among researchers as well as with the public, we have offices of astronomy for education, outreach, development, and young astronomers, as well as a center to protect the sky from radio and optical interference from large-scale communications networks. We also have 9 scientific divisions, 34 commissions, and 48 working groups to carry on our research. We have committees focused on diversity and inclusion, women in astronomy, young astronomers, and professional amateur collaborations so that we build towards an inclusive community. The best science will be achieved when we share ideas from all. Besides astronomical research, we work to foster connections with other aspects of society. The tools and techniques of astronomy are applicable to a wide range of technical careers, including those in computer science, industry, instrument building, medicine, health, and finance. These applications all help further United Nations Sustainable Development Goals. Indeed, a scientifically literate global society is our best hope for the future. I wish you all a wonderful Congress as you enjoy the astronomical
our next
lectures,
lectures by Anna
discussions, networking,
Riazulu.
and camaraderie during the coming
About
sessions
black
this
holes, and
week.
I think you will
Remember that we are all
present it better
together
than me,
under
so
one sky.
thanks.
Thank you.
Okay, thank you. So before starting, I have to apologize. I did not realize that this I was for international, so I took my French slides. So everything will be written in French, and I will try to illustrate this by reasonably well pronounced in English. Okay. Okay, so the title is Journey Around and Within a Black Hole. So the talk will be in 2 parts. The first part will have 3 subparts. What is a black hole? Where do they come from? And how do we detect them? And the second part is the much funny part of the talk, is what would we see and what would we feel should we be around a black hole. So I will be quite fast on the first part because these are things that are fairly well known by most of you. And the fun part will be this one, where we will try to simulate what happens if we want to commit suicide by diving into a black hole. So it's a very interesting thing. It's a useless but interesting thing. Okay. Okay, so in order to define a black hole, you first start from the concept of escape velocity. Okay, at the surface of a spherical body, you have a specific velocity, which is the one which allows you to escape the gravitational field of an object. You now know that to escape Earth's gravity field, you need to have a rather small velocity, a little bit above 11 kilometers per second. And with the sun, it's much larger because the mass over ratio of the mass over radius of the sun is much larger. Okay. Now, more than 2 centuries ago, two people asked the question: what happens if the escape velocity at the surface of a body is equal or larger than the velocity of light? So this was a good question, but it appeared to be useless, because if you do the calculation for a solar mass object, then the radius must be smaller than 3 kilometers, which induces a huge density of several tens of billion tons per cubic centimeter. Okay, so 1 million Eiffel Tower in this volume. Okay, so it seems completely crazy. Now, the density threshold which allows you to make a black hole depends on the total mass. And the larger the mass, the lower the density. So how much mass do you need in order to make a black hole from an Earth density object? So the result is around 60 million of solar masses. So the conclusion of this is that if you want to build a black hole, either you have huge densities or huge amounts of mass, which is the reason why at that time, so the end of the 18th century, the concept of black hole was of purely academic interest. And as you know, the situation changed during the first third of the 20th century. We discovered stellar remnants, which are much more dense than stars. So first, white dwarfs. So in this picture, the interesting object is this one, not that one. So this is Sirius A, and this is Sirius B, whose mass is not very different from that one, but whose luminosity is 4 orders of magnitude lower, because this object is much smaller. So it has a much higher density, 1 ton per cubic centimeter. And the escape velocity at the surface of a white dwarf is around 6,000 kilometers per second, so 2% of the speed of light. And then 1 or 2 decades later, people thought about the concept of neutron stars. As soon as the neutron was discovered in the lab, people thought about what a neutron star would be. They understood that it would be a very dense object. And the neutron star of a solar mass object would be a not so small fraction of the speed of light, or 2/3 of the speed of light. So people predicted and then observed neutron star, and then it became pretty clear that objects with a very large escape velocity existed, and so that black hole could exist as well. Now, to prove that black hole exists is a complicated matter, because I show you most of the steps. So you have to understand what a star is. Basically, it's like the sun. Then understand you need to do astrophysics and trying to understand what is the interior of the star, what is the density, the temperature, the pressure profile. Okay. You have to understand what is the source of energy of the star. So we know today that it's nuclear fusion, but it was not known 1 century ago. And once you have all this, you understand that the star evolves in a very different manner as a function of their mass. And you can begin to guess that high mass stars can give birth to black holes. Okay, once you have done that, you have a second problem. You have a n+1 problem, which is that it's quite difficult to define a black hole, actually, because the concept of escape velocity supposes that you have an object which has a mass and which is attracted by a star or whatever because it has a mass. But light does not have mass at all. So what does it mean that light cannot escape an object? You can't answer this question using Newtonian physics. So you need to use general relativity, but even though general relativity was found in 1915, it was correctly understood only decades later, and especially when it dealt with black hole. So the correct description of black hole was given 50 years after the discovery of general relativity and was initiated by the fact that stellar evolution gave hints that massive stars could build black hole. And once you have all this theoretical background, you need to do some observation to confirm this, and this was difficult because black holes are very discrete objects. They are very difficult to detect, and they don't form very often. So people had to deal with 21st century technology, but also had to use some very old observation, in particular one which was made in the 11th century. And if you love astronomy, you already know what this 1054 year means. Okay. So what do we know about black holes? So I won't explain how we know it. I will just give a few figures. So you have two types of black holes, stellar mass black holes. We know more or less their mass. We know how they formed, but we don't know how many there are, just because they are very difficult to detect. And to give you a few numbers, we are pretty sure that there are at least 30 millions of stellar mass black hole in our galaxy, but we only know 30 of these. So 1 over 1 million black holes are known at best, because this black hole population could be above this 30 million figure that I gave you. Okay. And then you have a second population, as you know, which are supermassive black holes, which are almost the opposite. The mass is very different, much more massive. The number is very different, much less numerous. You have one supermassive black hole per galaxy. And contrarily to the stellar mass black hole, we don't know how they formed. There is such a gap in mass that we have good reason to think that they did not form using the same channels, but basically we don't know how the details. So even though we don't know how supermassive black holes form, they are the most easy to study because they have a larger sphere of influence, and so they are easier to detect and to study. Okay. Okay, so I will talk about stellar black holes here. How do they form? Well, basically, you have to understand that a star is something that collapsed, starting from a very large size, and then which stabilized and became a star. So initially, a star is a cloud of whose size is maybe 1 light year across. Okay. It contracted because of gravity, and then the temperature increased high enough so that it could start to ignite nuclear reaction. And the extra energy given by the nuclear reaction produced radiation pressure, which prevented the collapse to go further. So the collapse stops as long as the star shines, but the star cannot shine eternally. The amount of energy is finite, just because the mass of the star is finite. So once the star stops shining, it contracts again. And this immediately tells you that stellar remnants are always more compact than the star that existed before. Okay. So stellar evolution in one slide is this. So you start from what you call a protostar. If the mass is not high enough, less than 8% of the mass of the sun, it actually does not ignite. The central temperature does not allow you to have a long-lived nuclear reaction. So you build something that is called a brown dwarf, which is some sort of heavy planet. It's not much bigger than a planet, it's heavier. And it's not interesting. Between 8 and 50% of the mass of the sun, you have red dwarf, that is a low mass star, which shines very dimly, but which will shine for very long. Okay, the most short-lived red dwarfs have a life expectancy 4 times longer than the actual age of the universe. So no red dwarf has already ended its life. Okay? So this is not what we are interested in. What is more interesting is solar mass star, between 1/2 and 8 solar masses. Then you have solar mass star, which will experience a series of nuclear stages. It will experience a rather short epoch where its size will increase a lot. Because of this, it will lose a lot of mass, and then will stop shining. So that when it loses its mass, it's called a new planetary nebula, not because there is any planet involved in the process, but because the nebula is rather spherical. So on the sky, it looks like a disk, but it's nebulous. It's not very bright. And in the center of the planetary nebula, you have the dying star, which shrinks till it reaches something which is around the size of the Earth. So a solar mass star transforms into a white dwarf, which is a solar mass object of planetary size. Okay, so it's much bigger than a black hole, so it does not evolve into a black hole. And the most interesting part is when you have a very high mass star, so between 8 or 10 solar masses till the maximum mass that you can have with a star. The figure is not known. So as you know, these stars experience a much larger number of nuclear stages. And at some point, for a very subtle reason, there is an instability in the core of the star. The core of the star collapses, and then the outer layer falls on the core of the star. The core of the star is very difficult to compress, so they bounce on it, and the shock wave that results from this shock has enough energy to dissipate all the outer layers of the star. So from the point of view of an external observer, the star seems to explode, so it's called a supernova. But what initiates the process is the implosion of the. So this is what we are interested in, because what happens to the core of the star which collapsed? So people think that initially it forms a neutron star. So a neutron star is a sort of gigantic atomic nucleus, but whose nuclei are almost only neutrons, and they are packed against each other as much as in an atomic nucleus, except that you don't have a few dozens of nucleons, but a few 10 to the 57 nucleons, okay? So this is what initially forms, and when the outer layer falls on the core, they slightly compress it. And so if there is enough mass that falls on it, it can shrink even more the neutron star. And because the neutron star has an escape velocity which is not very different from the speed of light, you don't need to compress a neutron star much to transform it into a black hole. So the simple way to describe it is that if the star is between maybe 10 and 15 solar masses, the neutron star survives to the core collapse. And if it's more massive, it forms a black hole. But there are a lot of discussion on whether there is a very strict threshold or whether there are some other parameters which determine whether you form a neutron star black hole. But basically, the more massive the star, the more likely it's that it will end its life into a black hole. Okay, so the two end stages of stars, in most of the case, because 99.9% of the stars have a rather small mass, less than 8 solar masses. So it gives a planetary nebula and white dwarf, and in 0.1% of the case, you have a supernova, and possibly within it either a neutron star or possibly a black hole. Okay. So supernova are very spectacular events. Only massive stars give birth to supernova, and very massive stars are already very bright before becoming a supernova. And you see here the difference between the before and after stage of a supernova. Okay, so this is a small part of the Large Magellanic Cloud. So this picture, I think, was taken in June 1986. So you see individually the brightest star of this region of the Large Magellanic Cloud. This star is clearly among the brightest one, but it's not much brighter than the others. And there is nothing in this star that lets you think that it's about to explode into a supernova. And 8 months later, here is what people saw at this point. So a supernova is a very bright event. Sometimes people say that the brightness of a supernova is more or less equivalent to that of the host galaxy. So this is slightly exaggerated, but it's a few percent of the luminosity of the galaxy, which is already quite impressive. Okay. So supernova are very rare event. We consider that in Milky Way we have between 1 and 2 supernovae per century on average. Unfortunately, the last supernova in our galaxy was seen in 1604. So are we unlucky that there were no supernova for 4 centuries? So the answer is no. The problem is that our galaxy is the galaxy where it is the most difficult to detect supernova, because our galaxy is a disk. In this disk, you have stars and you have dust and gas, and this dust absorbs light. So even if you have a very bright event as a supernova, if the supernova is in the opposite side of our galaxy, it will be completely dimmed by the dust that is in between. So there is nothing incoherent or surprising that we saw probably 8 supernova in 2000 years, whereas there were between maybe 20 and 40 supernovae in our galaxy in this stage. So we probably miss more than 60% of the supernova. So when is the next one? I don't know. The first time I gave this talk, it was 15 years ago. So there were 201. Then I have to change, and I put 202. And in 6 years, I probably will put 203. So I cannot guarantee that you will see it in the next days. But the more you wait, the more it's likely to happen. So you just have to live long, okay? And it will happen. Okay. So unfortunately, none of these known supernova gave birth to a black hole. Some were supernova of different type that I told you. They were not core collapse supernova. And the core collapse supernova, such as this one, for example, gave birth to a neutron star. So you see it by eye. So this is the Crab Nebula. So this is the supernova that exploded in the middle of the 11th century. And you see by eye that there is a neutron star in it, because once the supernova has exploded, there is no source of light to illuminate the remnant from the interior, okay? So if you see the interior of the remnant, it's because you have some very energetic process that is at work, and you shouldn't see that if there were a black hole inside. There is a neutron star here, and the activity of the neutron star produces a lot of cascading electromagnetic events which give rise to this center brightened remnant. So by eye, you already know that there is no black hole in this. Okay. Nevertheless, we are quite certain that some supernova can give birth to black holes. So the most convincing example, for a reason that I never understood clearly, happened in galaxy M100 in 1979. So for some reason, people can study from a large distance the remnant and get convinced that the remnant has not the property of a remnant with a neutron star in it. And the even more convincing proof that massive star can evolve into black hole is what is called failed supernovae. Okay, so these are 2 pictures of the same region of the most active nearby galaxy, which is NGC 16946. So this galaxy has experienced 12 supernovae since 12 decades. So on average, 1 supernova per decade. So this gave people the idea to monitor all the massive stars of this galaxy. And so these two pictures by the Hubble Space Telescope with an upgraded version of the instrument this time, show you that there is a star that has literally disappeared from the field of view, but no supernova was recorded in this part of the galaxy. So this very massive star disappeared in a few years, and people think that it was a failed supernova. So the core collapsed, and all the rest of the star fell on the core, transformed it into a black hole, and the black hole swallowed the star from the interior in a few days. So the star disappeared from sight in a very short amount of time. So we are pretty sure that this is a massive star that gave birth to a black hole from the fact that we did not see the supernova. The only way not to see the supernova is that there is no bounce, and therefore that there is no neutron star that forming it. Therefore, it's black hole. But as you see, this is quite complicated. Okay. So we know that black holes exist, even if it's difficult. And the way we study them is basically the interaction between a black hole and its environment. So I won't spend too much time on it, but stellar mass black holes are detected by the fact that you have often stellar binary systems. Stars evolve all the more fast that they are massive. So if you have a normal star and a massive star, this will end into a normal star plus a black hole. And if this normal star grows because it reaches the red giant phase, then part of the mass of the star will be attracted toward the black hole. It will form a disk around it, which is called an accretion disk. And you will detect the black hole from the luminosity of the disk. So an active black hole, a black hole which is swallowing matter, is a very bright object because the matter which is spiraling toward the black hole becomes heated to very high temperature and is visible. Okay. So this is the way we detect stellar mass black hole. We can detect supermassive black hole just by looking at star orbiting around it. So this is the case for the supermassive black hole of our galaxy. I can probably show you this. So this is a small movie that was made between 1992 and 26. Okay. So this is a picture. This is a movie constructed from pictures of the galactic center, and from one picture to the other, we show only what has changed. Okay, there are plenty of field stars which are uninteresting, and we show here only the moving things. And the trajectory of these stars are compatible with Keplerian trajectory with a focus which is here. Okay. So from Kepler law, you can determine how much mass you need to put at this red cross in order to explain the star motion. The answer is 4 million solar masses. And the periastron approach of this star is rather small. It's a few tenths of billion kilometers, so slightly more than the solar system, but not much. And in this region, you don't have one solar mass, but 4 million solar masses, which don't emit any significant amount of light. So this is the best visual proof that that supermassive black hole exists. We don't know how to form a 4 million solar mass black hole. Well, we have some ideas now. We don't know the details of the process, but we know that they exist for sure. Okay. So the situation has changed about black hole recently because, as you know, we are now able to see black holes. So I don't have time to give detail, but we are able to make pictures of black holes. So it's very difficult because black holes are very small as compared to their distance. So you need to do some to have some very, very high resolution observational devices. And to give you an idea, this donut-shaped thing has the same angular size of a big apple, which would be on the surface of the moon that you would try to see from Earth. So even if you don't know much about optics, you can guess that it's definitely difficult to see an apple on the moon. Okay. So we are quite lucky because we can see two black holes, the one of our galaxy and a much bigger black hole, which is much further, but the ratio between the distance and the mass and the size is the same. So this is the black hole of the nearest giant galaxy, which is Messier 87, and this is the black hole of our own galaxy, and it is the same field of view. Okay, so this one is 2,000 times smaller than that one, but it's also 2,000 times nearer, basically. So we see the same thing, but I think you will agree that it's quite ugly. Okay, it's very moving, but okay. When you see nice HST picture or JWST picture, okay, completely blurred. It's not very nice. So this is the reason why I tried one day to ask the question, what if we could see a black hole? Okay. So this is what I'm going to show you. But before this, so I won't talk about gravitational waves. Before this, I have to address one point, which is the following. Suppose that you are very near a black hole and you ask the question, what does it look like? There are basically two types of observers you could consider. The first is an observer which is at rest in front of the black hole at any distance you want. And for some reason, this observer has the technology that allows it to be at rest with respect to the black hole despite the huge gravitational field. And then you could consider another situation where you are orbiting around the black hole at the same distance. So these two observers are at the same position in space, but have very different velocity. You have an observer which is at rest, and one which is orbiting, but at a very high velocity, because in order to orbit near a black hole, you have to have a very large orbital velocity. So this asks the question, does the sky look the same when you change the velocity of the observer? And the answer is no. There is one thing you all know, it's Doppler effect. Okay, if I'm going very fast toward the light source will be blue shifted. So the color of the source will change. The intensity of the source will change as well. The light flux increases when you decrease the distance to the source. Okay? But you have something that is even more important that you don't think at first, it's aberration. Okay? So in order to understand this, think about the rain. Okay? You're in a car, you're at rest, and it's raining, there is no wind, so the rain is falling vertically. Okay? Now you begin to drive, and the rain does not seem to fall vertically because what you see is the velocity of the rain with respect to the car. So there is a vertical component, the velocity of the rain with respect to the ground, plus an horizontal component, which is the velocity of the ground with respect to the car, the opposite of the velocity of the car. And the faster you go, the larger is this horizontal component. So if you are at rest, the direction of your raindrop is this, and if you are very fast, the direction of the raindrop is this. Okay. Now, what is true for the rain is true for the light. So suppose that you have a star that is at the zenith when you are at rest. If you go very fast, the star won't look at the zenith, but at the lower elevation. Okay? And the faster you go, the closer the star will seem to be in terms of angular distance with respect to the direction of your motion. Okay? So when you accelerate, all the star is going to shrink toward your direction of motion. So this is very confusing, and I'm going to show you this first. Okay? So we are going to have a very violent acceleration, which is actually going to kill us, but we forget about that. Okay, can we switch the light off, please? It will be funnier. Okay, so we are going to go into the center of the screen. Okay, so the sky I show you is the one you see from Earth. I just remove the sun because I don't need that light source, and I'm heading toward epsilon Eridani, I think. Okay, so you have the velocity here. So we are already at a quarter of the speed of light, and what you see visually is aberration. Everything seems to shrink. We are heading toward this direction, but we have the visual impression that we are receding because of aberration. Okay. Then after a while, you notice that the sky is brighter. This is the flux effect I showed you. And then even later, you begin to see the color of the star that changes. So why is the Doppler effect so inefficient in a sense? Because stars are not monochromatic emitter. They emit like a black body, so they have a very broad spectrum of emission. So when you shift the overall emission spectrum of the star, you change the color, but rather weakly. Okay. So our Betelgeuse was red, now it's white, but it took quite a long time to happen. Okay. So I insist on the fact that we are almost at rest. Our distance to this star has not changed at all. We have traveled 1 light minute. So maybe 15% of the Earth-Sun distance. So we did not travel any significant portion of a light year. So we can consider that stars are completely at rest. Or our distance to the star has not changed. What changes here is only because we have changed our velocity, not our position. So there is no parallax in this. Okay. Okay, so a nice feature of aberration is that it distorts the sky, but it transforms circles into circles. So the Milky Way is a disk. We see the disk from the inside, so it's a large circle in the sky. Because of aberration, the angular diameter of the disk changes, but it's still a circle. Okay. So the impression is that we are receding away the Milky Way, which is a ring, but it's not at all what happens. We are still in the disk of the Milky Way because our position has not significantly changed, but we have the impression that it's a ring we are receding away from. Okay, so it's quite subtle. And the other conclusion of this is that light speed travel is very boring, because when you go very fast, actually all the sky is shrunk into a very small portion of the sky, and you just don't see anything. You will notice that you have traveled some distance when you are going to decelerate, because then sky will unfold, and you will notice that the final position of the star is not the same at start, because you have moved. But when you are at 99.9% of the speed of light, you don't notice that the star are moving, or that you are moving with respect to the star. Okay, it's only when you are decelerating that you notice. Okay, it starts again, but it doesn't matter. Okay. So now, what happens if you put a black hole into the story? Okay. I spare you from this. Okay, so a black hole is a region of space from which light cannot escape, but as any source of mass, a black hole is something that is deflecting the trajectory of objects or light. So suppose you are here, there is a black hole here, and you look toward the star which is far away behind the black hole. So the actual position of the star is this, but you won't see the star in this direction because the light ray that comes from the stars along this trajectory will be either swallowed or deflected by the black hole. So you won't see the star from photons which come from this direction. The photons that will reach your eye will, for example, take this direction, so they seem to miss the place where you are, but they will be deflected by the black hole and reach your eye. But your eye does not have any information that this photon has been deflected. So from your point of view, the photon comes from here. And so there is some apparent position of the star, which is which is here. You see the star here, whereas it is here. So the point is that the apparent position of the star is in terms of angular distance further from the black hole than the actual position of the star. And because black hole can deflect light by an arbitrary amount, you have a second light ray that goes below the black hole and that is deflected as well. So you'll see two images of the star which are around the actual position, but you don't know where the actual position of the star. So when instead of light rays you consider bunches of light, you can show that the amount of light that you receive here is much larger than the amount of light that you would receive from the black hole should it not from the star should the black hole not be there. So you will have an amplification of the light, and this is what we call lensing, gravitational lensing. So I show you the gravitational lensing by a black hole from large distance. Okay. So I still remove the sun from the stage. I put a black hole inside. So the sky you see, the one you see from Earth. This is just for fun for you to realize that the sky is heavily distorted. So you have Sirius that is on the bottom of the screen. Here you have Orion, Taurus, and here you have M42, the Pleiades. And you don't recognize it because you have actually two images of this cluster, and those two images are heavily distorted, so they are elongated. And when you let the black hole travel in front of the Pleiad, the black hole is at a short distance and the stars are very near, you see that all the stars of this cluster seem to try to avoid the black hole. This is not the case, of course. The stars don't move, but the images of the star that reach your eye do. Okay? So when you have all this in mind, we can play really by saying, hey, what would happen if I were much nearer than a black hole? And for example, if I was orbiting at some distance. So I am orbiting around the black hole counterclockwise. And instead of looking in my direction, I'm looking toward the center of my trajectory. So from my point of view, it's like the celestial sphere that transits behind the black hole, okay? And should the black hole not deflect light, I would see every picture of a star translate horizontally from the left to the right. But I don't see that. Because when a star becomes quite aligned with the black hole, I will see two images of this star, and I will see distorted patterns. So this is the Southern Cross, this is the Southern Arclet, and this is nothing. Okay. So each of the stars has an image. You see it from this one. This one is this one, and so on. Okay. And once the Southern Cross is no longer behind the black hole, I more or less recognize the pattern. Okay. So the closer you are in terms of angular distance to the black hole, the more distorted you are. But otherwise, you can recognize. So here we are at a reasonable distance from the black hole, whereas our orbital radius is 15 times the black hole radius. So our velocity is not very large. It's only 18% of the speed of light. So that the spatial relativistic effects I showed you are not very large. But we see them anyway because we are heading toward the right of the screen. So this part should be blue shifted and this part should be red shifted. So you don't see the blue shift and the red shift, but you see the intensity gradient. So it's dimmer here and brighter there. Okay. But it's not very pronounced because I don't compare the front view and the rear view. And my velocity is not very large in the context I'm in at the moment. Okay. So of course, we want to know what happens if we are nearer to the black holes. So let us reduce our orbital radius by a factor of 5. Okay. Now we are so near to the black hole that I don't show you the view toward the black hole, but toward our direction of motion. And my orbital velocity is half of the speed of light exactly. And here, even if I don't look toward the black hole, I just don't recognize anything to the sky. Okay? If I stop here and I ask you which part of the sky do you see, I would not insult you by betting that you won't recognize. Okay? So if you want to know, this is Betelgeuse, this is Sirius, this is Orion Belt, this is Rigel, and this is the Big Dipper. Okay? So why don't you recognize anything? The reason is that your sky is so much blue shifted, so that what you see is the infrared sky. Okay, and in the infrared sky, red stars emit much more light than blue stars. So in the infrared, Betelgeuse is a much brighter star than Sirius. So you don't recognize the stars because their relative luminosity are changed. And you don't recognize also things because aberration shrinks a large portion of the sky into a small patch. So you don't expect that the Big Dipper is so near Orion, but this is because of aberration. Okay? So it's extremely difficult to recognize where you are in such situation. So as we are orbiting around the black hole, Betelgeuse is no longer toward the direction we are heading to, and you are going to see that it becomes increasingly redshifted and it dims away and becomes less bright than Sirius, as you can expect. Okay, so everything is logical, but confusing anyway. Okay. Okay, can we go nearer to the black hole? Well, it's difficult because relativistic celestial mechanics tells you that you can't have a shorter orbital radius with a circular orbit. If you want to go nearer to the black hole, you need to have some elliptical orbit. So I show you what it is. It's quite funny. Okay. Okay, so here we are slightly receding away. We reach the apoastron, and our velocity is going to increase as we go closer and closer to the black hole. Okay, so it's a second Kepler law, the law of area. And at periastron, we go very fast. The sky is very bright. The angular size of the black hole is very large, and we survived. Okay, we are happy. So is this an elliptical orbit? Not quite, because orbits are elliptical in Newtonian physics, but in relativistic physics, you know that the periastron is shifting with time. Okay, so this was the first verification of general relativity, and actually this is something we are going to see by eye. Okay, so I'm going to stop at apoastron here. So when this R in the corner will be 50. Okay, we are at apoastron. What do we see of the sky? We see, I don't know in English, le cocher, and the Milky Way is slightly below. And this should be the northern sky, okay? I don't recognize everything because this is probably Betelgeuse here, and this may be Procyon, I'm not sure, okay? Nevertheless, okay, this is Capella, and Capella was around here at apoastron, okay? We do one more orbit. So in Newtonian physics, our orbital phase would increase by 360 degrees, but we are precessing, so it will increase by more than that. And at next apoastron, we are here. And here what we see is the southern sky, okay? This is Southern Cross and so on and so on. And we are almost at the opposite of Orion. So we have been precessing by more than 100 degrees. So between two apoastron, our orbital phase has changed by 360 plus 110 degrees. So we have more or less a cloverleaf orbit, if you like. Okay. So you see by eye the relativistic precession of orbits. It's a very weak effect in the solar system. It took time for people to convince themselves that there was something going on with Mercury, but here you have a very large precession just because you have some extreme gravitational effect. Okay. Can we go closer? Yes, we can, provided that our ellipse is even more elongated. So we have a very large apoastron, and this allows us to have a much smaller periastron. And it looks like this. Okay, so we start from a large distance with a very small amount of orthoradial velocity so that we don't have a radial trajectory, okay? And because we start from a large distance, we can get a large velocity, which will allow us to pass very near to the black hole without diving into it. So here our orbital velocity at periastron will be sometimes like something like 71% of the speed of light, so 210,000 kilometers per second. And our distance to the black hole will be equal to its radius. So our altitude will be equal to the radius. So here we are going quite slowly, so the sky is not very bright. And as our velocity increases, of course, the sky is going to be very bright. So this is a very unstable trajectory. Don't try to do that because a tiny error in your initial direction could make you fall into the black hole. This is a very dangerous thing. And again, should it be a parabolic orbit in celestial mechanics, you would do half a turn around the black hole. But here, because of precession, you did several turns before going away. Okay? So if you want to go even closer, you need a hyperbolic trajectory. So hyperbolic trajectory is that you start from infinity with a non-zero velocity. Okay. So I start not from infinity, but from a fairly large distance at already 40% of the speed of light. And in this situation, the sky is already very bright. And this will allow me to go even nearer to the black hole. So again, the trajectory is very unstable. So it's very dangerous to do. But relativistic orbital mechanics allows you to do that. Okay. So the start of the simulation is rather boring. Okay, you go almost along a straight line, and when you will be very near to the black hole, of course, things will be a little bit faster. Okay, as you can imagine. And again, in a normal Newtonian hyperbolic orbit, your deflection is less than 180 degrees. And you here have the orbital phase, and you can predict that it will be much more than 180 degrees. We are going to do 4 turns around the black hole almost before being expelled. So in general relativity, it's called the zoom and whirl effect. Okay, you start from very fast, you turn a lot, and then you exit. Okay. So you can go even nearer, but it's completely uninteresting because if you want to go nearer, you need to have larger initial velocity, such that the sky is very bright and you don't see the black hole at all. Actually, you see it. It's here. But you barely see it. Okay, it's not very interesting. You can guess that there is something fishy going on because your velocity is changing. So if you are traveling along a straight line without any mass, your velocity should be the same. If it's increasing, is that you're heading toward a mass that you don't see. So you already know that it's a black hole. And it's not very clever because we are going to be very close to the black hole. I show you anyway. So from time to time, you have some flickering because you have some lensing effect that brighten the surrounding of the black hole. It's not the important part of the thing. Okay. It will be very, very short because of length contraction due to special relativity. I don't have time to give you the detail. And we did survive. It's a completely silly situation, but okay. So if you want to go nearer to the black hole, you have to use a non-geodesic motion. So you have to suppose that you get closer and closer to the black hole, and you have very powerful engine that prevents you from increasing your velocity. So I'm going to show you what could be a sort of soft landing on the surface of a black hole. There is no solid surface, but anyway, you can simulate what would happen if you try to reach the surface of the black hole at very low velocity. Okay? So this is my altitude. So when I am the surface, this is exactly 0. And I'm getting nearer and nearer to the black hole. Okay? So because the black hole is nearer, it's bigger in the sky. Okay? The angular size increases with the distance in a different manner than the usual trigonometric formula. But obviously, there is nothing weird with the fact that the angular size of the black hole increases when I'm getting nearer and nearer. At some point, because my field of view is something like 110 degrees, the black hole will be bigger than the field of view, and the front view will be completely uninteresting. Okay, I think you will agree. In a few seconds, everything will be black because you are looking in the wrong direction. Okay, so I continue this simulation by looking on the right. So actually, now the black hole is on your left, and I'm looking to my right. So my distance to the black hole is decreasing. The black hole is going to be bigger and bigger. And as I told you, the black hole pushes away the lights, the stars. So from your point of view, all the stars that are near the black hole are deflected so that their apparent position goes to the right here. Okay. So suppose that you don't know that this is a black hole. Okay. You don't know, you did not notice that it was deflecting light. You would say the moment where I am landing on the surface of the black hole is when the black hole silhouette will be exactly half of the celestial sphere. Okay, when you are on the surface of something, if you look down, you see the surface. If you look up, you see the sky. So the natural interpretation is that the moment where I am at the surface of the black hole, this would be a straight line. Everything at the left is the black hole. Everything at the right is the sky. Okay? And this is not what happened. Here I am still above the black hole. And the black hole seems to engulf me. So what is happening? If you're very near the surface and you have a horizontal light ray that goes toward you, this light ray will be deflected and be swallowed by the black hole before reaching you. So the only light ray that reaches you come from above. Okay? So this is very funny because a black hole is a spherical object. It's convex. But when you are very near the surface, it looks concave, and the visual impression is that you're inside a hole, whereas at this stage you are still outside. Okay, so there is something that you probably noticed, but that you will see better if we look at the rear view. So now the black hole is behind you, okay, and the black hole is going to engulf you from every direction. So as the distance decreases, just as in the other simulation, what you are going to see is that the sky is brighter. So why is it brighter? You are at rest in a potential well, and you go deeper and deeper in this potential well. And you see light, and you cross light rays that fall on the black hole. So these light rays gain energy as they fall into the black hole. So their velocity is always c, but their energy increases so that their frequency increases. So you see gravitational blue shift. So all the stars become blue shifted not because you are moving, because your velocity is very weak, but because you are deep within a potential well. So all the stars are going to be blue in the end. And this is a very bad news for you, because if the light has gained a lot of energy to reach you, this means that you will need to spend a lot of energy to exit. So this is very bad news. This is very worrisome. You already guessed that it was not a good idea to go to be there, but the fact that the sky is becoming brighter and brighter is really bad news. Okay? So don't do it again. Okay, so now I am at the part of the talk where I have to ask you something. Do you agree to commit suicide collectively with me? Okay. Okay, this is fun, but what happens inside? Okay, so is everything okay to commit suicide? Okay, no one I don't hear yes, but I don't hear no as well. So I consider that it's a yes. Okay. So we are going to dive into the black hole following a radial trajectory. Okay. So the approach phase is long and boring, and the interesting part, and when you are inside the black hole. So I am going to shrink the approach phase and to increase the length of the phase inside the black hole because it's more fun. And this is what it's going to look like. Okay, so we are falling on a radial trajectory. Okay, we are accelerating, so our velocity is going to increase, and the distance to the black hole is going to decrease. Okay. Now, as compared to the previous simulation, there is something funny that is going to happen. With respect to the static observer, we are going very fast in this direction. And because of this, aberration is going to shrink the size of the object and the size of the black hole as well. So there is something that is going to happen, is that the moment where we are going to enter into the black hole will happen when the black hole angular size is not that big. So in this situation, the moment where you enter into the black hole happens, whereas your visual impression is that you're outside. So it's completely the opposite. So as you may know, there is nothing special that happens when you enter into the black hole, when you cross the horizon. So I have put a green flash at the moment where we cross the horizon, just for you to notice that there is nothing different before and after. Okay. So the moment we are going to enter into the black hole is when its angular radius is 42 degrees. So it's like if you were at half of the radius of the star. Okay, here we are inside. Okay. You did not notice anything at this moment. So the front view is not very interesting, just as previously. So we are going to see the view from the right. So the black hole is here. We are heading toward the black hole. Because there is aberration, because our velocity is increasing, the stars which are behind us are pushed to the right and go toward the front direction. But because we are near the black hole and the black hole angular size increases, the stars that are near the black hole are pushed in the other direction. So what you see, and this is really what you should see, is that all the stars are going to pile up each against each other. And for some reasons that are fairly subtle, this is the visual illustration of the tidal effects that at some point of this simulation are going to kill you. So your physiological impression is that you are stretched along the horizontal direction, the radial direction is here, but the visual impression is that everything is shrunk along this direction. The reason for this is a little bit subtle, but that's the story. Okay. So at some point you are killed by tidal effects. When exactly it depends on the mass of the black hole, but it happens anyway at some point. Okay, so at this stage, I could say, okay, you are dead. The talk is over. Thank you for coming. And this is not very fun. So I propose you something else that you may recognize immediately. I should propose you this. Okay, does anyone guess what you see here? So it's not a Kerr black hole. It's something that looks like a black hole, but obviously light can escape from it. It's a wormhole. Okay, we are orbiting around a wormhole. So we see another universe or another part of the universe. And we have a very heavily distorted view of this other universe because the light that traveled through the wormhole was a little bit, even more difficult. So this is an example of that. There are several types of wormholes. So this is one example. It's not the one of interstellar, but it does not matter. Okay. And to conclude my talk, I propose something even more fun, that crossing the wormhole. So crossing the wormhole is something very difficult to simulate. Well, first because it's not easy intrinsically, but also because there are things that happen in more or less any direction. So a flat screen is not appropriate. So what I did is that I did a planetarium version of it. So I'm going to show you on a flat screen the planetarium version of a wormhole crossing. Okay. So what you see is half a sphere, is a circle, and you have to imagine that this disk is projected on a hemispherical screen, okay? So I show this from time to time in Paris Planetarium next November, probably, maybe in October. And we are going to cross this wormhole here. So it's a wormhole that is fairly complicated. So what you are going to see is very weird. Fortunately, time is running out, so I don't have time to explain you all the detail. But the nice thing that even if you don't understand, this is quite beautiful. Confusing, but beautiful. And more beautiful than confusing, I think. So we are inside a wormhole. We see, for some reasons, another universe we can't reach. It's in our past light cone, if you like. When we are going to see in the most inner part of the wormhole, this universe is going to disappear from sight. We see only our universe with new distortion patterns, which more or less is the visual translation of the fact that the center of a wormhole is repulsive instead of attractive with respect to gravitation. Here we are going to, we begin our exit journey. So we see again this second universe that does not matter. This second universe is going to disappear a second time. And at this point, a new universe is going to appear. It's the universe we are going to exit in. And this new universe is going to somehow swallow all the celestial sphere except a small part. So we are in the grid universe. Okay, this is a coordinate grid. And outside the black hole, we see our universe. Inside the wormhole, we see our own universe. Okay. So it's confusing, but it has a meaning. At least general relativity tells us that it could look like this, despite the fact that there is no negative mass or whatever, which makes it probably impossible for wormhole to exist. But should it exist, it could look like this. Thank you.
So, thanks, Alan. If there is some questions, so because the building is going to close at 8 o'clock, maybe you can just take question at the front of the scene, so we can start to pack up everything. Thank you, everyone. And tomorrow morning it will be at 9 o'clock, so be in advance here. It will not be in this room, and not even in this building, but on the 45 of Ulm Street. So it's 100, 200 meters ahead in that direction, in the street you come from. Thank you, everyone, and see you tomorrow.
Okay, so if you have some question, I'm still here for a few minutes before the door close. I can you can ask questions. How much time? So actually, as long as your black hole or wormhole is spherically symmetric, you have to pre-compute things, and you can probably do something in real time. So you could do probably a flight